Hello there, and welcome to our channel, a place where curiosity slows down, science stretches out comfortably, and big ideas are allowed to settle gently rather than rush past. Wherever you are right now, whether the room around you is quiet or softly humming with the end of the day, I'm glad you're here. Tonight we're going to spend some time with a story that begins in cold silence and immense stillness. The kind of stillness only ice can create. A story about a planet locked in frozen balance and about what happened when that balance finally gave way. Before we ease into it, take a moment to notice where you're listening from. Maybe you're in bed, maybe on a sofa, maybe drifting between wakefulness and sleep. And what time is it for you right now? Early evening, deep night, or perhaps the very edge of morning? It's fitting to think about time as we begin, because the events we're exploring unfolded over spans so long they're difficult to picture. And yet, when the moment finally came, some of the changes happened with astonishing speed. If you find this space calming, or if slow, thoughtful science helps you unwind after a long day, you're very welcome to like the video or subscribe. It helps this quiet corner of learning reach others who might need something steady and unhurried to listen to. And now, with nothing required of you except listening, let's begin moving backward into a colder world. Imagine standing on Earth, not as it is today, but as it was near the height of the last ice age. The air is sharper, drier, heavier with cold. Vast regions of the planet that are now forests, cities, and farmland lie buried beneath ice sheets thousands of meters thick. These are not small glaciers tucked into mountain valleys, but continent-sized masses of ice, slowly flowing outward under their own weight, pressing down on the land with a force that bends the crust of the planet itself. North America's capped by the Laurentide ice sheet, Europe by the Fennoscandian ice sheet, and similar frozen giants spread across Asia and the southern continents. From space, Earth looks brighter, whiter, quieter. Sea levels are dramatically lower because so much of the planet's water is locked away on land as ice. Coastlines sit far beyond their modern boundaries. Entire continental shelves are exposed, forming wide plains where waves once rolled. Land bridges connect places that today are separated by oceans. Humans and animals move across these bridges without ever knowing they will one day vanish beneath rising seas. For tens of thousands of years, this frozen world persists. Ice advances and retreats slightly with subtle shifts in climate. But overall, the balance holds. When temperatures remain low, snow accumulates year after year, compacting into ice faster than it can melt away. The glaciers breathe slowly, expanding and contracting like massive, patient organisms. Rivers root themselves around walls of ice. Wind patterns shift. Life adapts to the cold rather than escaping it. And yet, beneath this apparent stability, change is quietly building. The climate system that maintains an ice age is not a single switch, but a network of interlocking processes. Earth's orbit wobbles slightly over tens of thousands of years. The tilt of its axis shifts just enough to change how sunlight is distributed across latitudes. Ocean currents rearrange themselves, transporting heat differently than before. Greenhouse gas concentrations rise and fall in small but significant amounts. None of these changes are dramatic on their own, but together they begin to loosen the grip of ice. At first, the warming is subtle. Summers grow marginally longer in the northern hemisphere. Sunlight lingers a little more intensely over high latitudes. Snow that once survived year-round begins to melt back slightly during the warmest months. Most of it refreezes when winter returns, but not all. A thin imbalance forms, barely noticeable at first, but persistent. As this continues, meltwater starts to appear at the edges and surfaces of the great ice sheets. Streams run across ice that once seemed solid and permanent. Water finds cracks, fractures, and weaknesses slipping downward, lubricating the base of the ice where it meets bedrock. This water does not simply disappear. It collects. It pools. It begins to gather behind walls of ice that act like natural dams. The scale of these meltwater reservoirs is difficult to grasp. Some of them grow into lakes larger than many modern seas. They press outward and downward with incredible force, held back only by ice that was never meant to restrain liquid water indefinitely. The ice dams holding these lakes are not static structures. They creep, fracture, and thin under pressure, responding both to the weight of the water behind them and to the warming climate around them. For long stretches of time, nothing visible happens. The lakes remain contained. The ice holds. The world stays cold enough that the balance, though strained, does not fully collapse. From the perspective of a human lifetime, everything would appear unchanged. From the perspective of the planet, however, tension is mounting. Then, at certain moments, the system crosses a threshold. Ice, despite its apparent solidity, behaves more like a slow-moving fluid under enough pressure. When meltwater forces its way beneath an ice dam, it can lift the ice slightly off the ground, reducing friction. Once that happens, the dam weakens rapidly. Water rushes through narrow channels, carving them wider by sheer force. Flow becomes flood. Containment becomes release. What follows are events so vast and sudden that they reshape entire regions in days or weeks rather than millennia. Walls of water surge across the land carrying ice, sediment, boulders, and soil in chaotic motion. Valleys are scoured down to bedrock. Hills are stripped of loose material. River systems are rerouted entirely, their old paths erased and replaced by new ones carved in moments of violence. These floods do not happen once, but repeatedly as ice dams reform, fail again, and release more stored water. Each flood transfers enormous volumes of fresh water into the oceans. Sea levels rise not smoothly, but in pulses. Shorelines retreat inland. Low-lying ecosystems drown. Ocean circulation patterns shift as cold. Fresh water disrupts established currents that once distributed heat around the globe. Climate responds in complex ways, sometimes warming overall, sometimes snapping briefly back toward colder conditions before continuing its longer trend toward thaw. For early humans living near the margins of ice and water, these changes would have been profound and frightening. Landscapes they relied on could disappear within a generation. Rivers could swell beyond recognition. Familiar coastlines could vanish beneath advancing seas. Memories of overwhelming floods would be passed down orally, shaped into stories that linger long after the physical evidence eroded. And yet, from a broader perspective, these floods play a critical role in ending the Ice Age itself. By rapidly removing ice from the continents and transferring it to the oceans, they accelerate the planet's transition toward a warmer state. Ice sheets thin, fragment, and retreat. Albedo, the reflectivity of Earth's surface, decreases as white ice gives way to darker land and water that absorb more sunlight. Feedback loops kick in, reinforcing the warming trend. the frozen world loosens its hold. What's remarkable is that none of this requires catastrophe in the cinematic sense. There is no single apocalyptic moment, no instant collapse of ice everywhere at once. Instead, there is a series of releases, adjustments, and responses spread unevenly across time and geography. Some regions change abruptly, others lag behind. The planet adapts in fits and starts, always moving toward a new equilibrium, but never along a perfectly smooth path. For now, it's enough to hold the image of a world balanced between ice and water, tension quietly building beneath the surface, unaware of how close it is to letting go. At the height of the last ice age, Earth was not a hostile wasteland, but it was a profoundly different place, shaped by cold in ways that are hard to fully imagine from a modern perspective. The planet was familiar in outline. The continents sat where we recognize them today, yet almost everything about their surfaces, climates, and rhythms had been altered by ice. This was not a brief, cold spell or a dramatic winter stretched across a few generations. It was a long-standing state, a deep climatic condition that endured for tens of thousands of years, long enough to feel permanent to anything living within it. Temperatures across much of the globe were several degrees lower than today on average. But that number alone doesn't capture the experience. Cold is not just a measurement. It shapes wind, moisture, soil, vegetation, and the way light interacts with the land. In this colder world, winters were longer and harsher, summers shorter and weaker. Snow that fell in high latitudes and mountainous regions often failed to melt completely, even during the warmest months. Year after year, that surviving snow compacted under its own weight, slowly transforming into ice. Over centuries, then millennia, these layers thickened into immense ice sheets. These ice sheets were not static slabs frozen in place. They flowed imperceptibly slow to the eye, but relentless in their movement. Ice behaves like a solid over short time scales, but under constant pressure, it deforms, spreads, and creeps outward. The weight of kilometre-thick ice pushed outward from its centers, grinding rock beneath it into fine powder, flattening hills, and carving the land into new shapes. Entire regions of North America and Northern Europe lay buried beneath this slow-moving mass. Their original landscapes preserved only as memories, locked under ice. The presence of so much ice on land reshaped the entire planet's water system. Water that would normally circulate through oceans, rivers, clouds, and rain was instead trapped in frozen form. As a result, global sea levels dropped by more than 100 millimeters compared to today. Coastlines extended far outward, revealing wide plains that had once been seabed. Rivers cut deeper into exposed continental shelves, forming valleys that are now submerged. In some places, land bridges emerged, connecting continents and allowing animals and humans to move between regions that would later become isolated. The atmosphere itself responded to this frozen configuration. Colder air holds less moisture, so large portions of the Ice Age world were drier than today. Even in regions covered by ice, deserts expanded in some areas, while others became cold steppes dominated by grasses, mosses, and hardy shrubs. Forests retreated southward or disappeared entirely from high latitudes, replaced by open wind-swept landscapes. Dust, carried by strong winds, settled onto ice sheets, darkening their surfaces slightly and subtly, influencing how much sunlight they absorbed. Life adapted not by resisting the cold, but by fitting into its patterns. Large mammals with thick fur and layers of fat roamed the plains, grazing on sparse vegetation. Smaller animals burrowed or migrated seasonally. Humans learned to survive at the margins of ice, following game, crafting clothing from hides, and using fire not as a luxury, but as a necessity. The Ice Age was not empty of life, but it demanded constant adjustment and awareness. Resources shifted with the seasons, and stability was relative rather than absolute. Despite its severity, this frozen world was remarkably stable over long periods. Climate did not remain perfectly constant, but it oscillated within bounds that kept ice dominant. Colder phases saw ice sheets advance, creeping farther south, while slightly warmer intervals allowed limited retreat. These fluctuations occurred over thousands of years, slow enough that ecosystems could reorganize around them. From the perspective of any single human lifetime, the ice seemed eternal. What sustained this state was a delicate balance of factors. Earth's orbit around the sun is not fixed. It changes subtly over time, in predictable cycles. The shape of the orbit shifts from more circular to more elliptical. The tilt of Earth's axis varies slightly. The timing of seasons relative to Earth's position in orbit changes. These cycles influence how much sunlight reaches different parts of the planet at different times of year. During the Ice Age, these orbital conditions favored cooler summers in the northern hemisphere, preventing winter snow from melting completely and allowing ice to persist and grow. Greenhouse gas levels also played a role. Concentrations of carbon dioxide and methane were lower than today, reducing the atmosphere's ability to trap heat. This cooling effect reinforced the growth of ice, which in turn reflected more sunlight back into space, amplifying the chill. The planet entered a feedback loop, where cold supported ice and ice supported further cold. Ocean circulation patterns were different as well. With lower sea levels and altered wind patterns, currents that today transport heat toward the poles behave differently. Less warmth reached high latitudes, further supporting the persistence of ice sheets. At the same time, cold, dense water formed more readily and sank, influencing deep ocean circulation in ways that rippled through the global climate system. Under all this ice, the planet itself responded. The immense weight of ice sheets pressed down on the crust, depressing it by hundreds of meters in some regions. Land beneath the ice sank slowly, while areas beyond the ice margin sometimes rose slightly in response. This deformation of the crust altered drainage patterns, redirecting rivers and creating basins where meltwater would later collect. The Earth's surface was not a passive stage for ice, but an active participant, bending under the load and storing potential energy that would matter later. One of the striking features of this frozen era is how quiet it must have seemed in many places. Thick ice absorbed sound. Vast regions would have been dominated by wind, occasional cracking ice, and the distant movement of glaciers. Rivers ran at the edges of ice sheets, swollen during brief summer melts, then reduced again as winter returned. Vegetation grew slowly. Change happened, but on time, scales that encourage patience rather than urgency. And yet, this calm was deceptive. Stability does not mean permanence. Even while the Ice Age endured, the processes that would eventually end it were already in motion. The same orbital cycles that help create the cold were gradually shifting. Greenhouse gas levels, though, were not fixed. Ice sheets themselves, by their sheer size, were setting up conditions that made them vulnerable to change. Melt. Water produced during warmer summers had nowhere to go but outward and downward, probing the weaknesses in ice from within. As ice thickened and spread, it altered regional climates in ways that sometimes encouraged further melting at the margins. The edges of ice sheets were complex environments where ice, water, air, and rock interacted constantly. Sunlight absorbed by darker debris on ice surfaces could locally increase melting. Water pooling on ice could deepen fractures, carrying heat downward. These processes were minor at first, barely noticeable against the scale of the ice, but they mattered because they persisted. Over thousands of years, small imbalances accumulate. A fraction more melting each summer than freezing each winter begins to thin ice from the top. Meltwater reaching the base reduces friction, allowing ice to flow faster toward lower elevations where temperatures are warmer. Faster flow brings more ice into regions where melting dominates, accelerating loss. The system does not collapse immediately, but it begins to lean from the inside of the ice age. These shifts would have been almost impossible to recognize as meaningful change. To someone living beneath the ice's influence, the world still felt cold, harsh, and familiar. Glaciers still loomed. Sea levels were still low. The Great Plains still stretched where oceans would later return. Yet, the balance that held this world together was no longer perfectly centered. This is the nature of long climatic states. They are maintained not by immobility, but by ongoing motion that happens to cancel itself out until it doesn't. Ice ages do not end because something dramatic suddenly appears. They end because the conditions that support them quietly adrift beyond the range where stability is possible. When people picture glaciers, they often imagine frozen stillness, immense white bodies, locked in place, unmoving and silent. From a human point of view, that impression makes sense. Stand at the edge of a glacier, and it appears timeless, as if it has always been there and always will be. But glaciers are not static objects. They are processes. They are motion stretched across time, so long that it becomes difficult to notice unless you learn how to look for it. A glacier is born not from cold alone, but from imbalance. Snow falls season after season and survives the summer melt. Each year, new snow presses down on the layers below it. Air is squeezed out. Snow crystals deform and fuse. Over decades and centuries, loose snow becomes dense firn, and firn becomes solid ice. Once the ice reaches a certain thickness, gravity takes over. The glacier begins to move. This movement is slow, but it is relentless. Ice flows downhill and outward from zones of accumulation, where snowfall exceeds melting, toward zones of ablation, where melting, sublimation, and calving dominate. The glacier is always gaining mass in some places and losing it in others. The balance between these zones determines whether a glacier grows, shrinks, or holds steady. This balance is never perfectly still. It shifts with seasons, with climate patterns, and with subtle changes in temperature and precipitation. In the depths of the Ice Age, glaciers and ice sheets operated like enormous lungs. They inhaled snow during long, cold winters and exhaled meltwater during brief, cool summers. The rhythm was slow, measured in years rather than breaths, but it was real. Expansion and contraction occurred continually, even when the overall system appeared stable at the surface. This breathing was visible in patterns of creases, melt channels, and layered ice. Snow accumulated in the interior of ice sheets far from their edges, building thickness over time. Under the weight of kilometers of ice, the lower layers softened and began to deform plastically. Ice crystals rotated and realigned, allowing the mass to creep outward. This flow was not smooth like water in a river. It was uneven, shaped by the underlying terrain and the internal structure of the ice itself. Beneath the ice, the ground experienced its own version of this movement. The immense pressure ground rock into fine sediment known as glacial flour. Stones embedded in the base of the ice acted like sandpaper, scraping and polishing bedrock. Hills were smoothed into rounded forms. Valleys were widened and deepened into broad U-shapes. The land did not resist so much as yield, slowly and permanently altered. But the most important part of a glacier's motion during the Ice Age happened out of sight at its base. Ice does not always sit frozen solid against the ground. When pressure increases and temperatures approach the melting point, thin layers of water can form between ice and bedrock. This basal meltwater acts as a lubricant, allowing the ice above to slide more easily. The more water present, the faster the glacier can move. This creates a delicate feedback. As glaciers thicken, pressure increases, producing more basal melting. More melting leads to faster flow, which transports ice toward warmer regions where it melts more readily. In a stable climate, these effects balance out. In a changing climate, they can amplify one another. During the Ice Age, this balance was mostly maintained, but not perfectly. Periods of slightly warmer summers allowed increased surface melting at glacier margins. Meltwater flowed downward through cracks and shafts in the ice, sometimes reaching the base. Even a small increase in basal water could speed up flow locally, causing glaciers to surge forward temporarily. These surges redistributed ice, thickening some areas while thinning others. Importantly, glaciers did not respond instantly to climate changes. They lagged behind them. A cooler period might increase snowfall, but it could take centuries for that additional snow to translate into noticeable glacier advance. Likewise, warming might increase melting, but the full retreat of a glacier could take hundreds or thousands of years. This lag meant that glaciers carried memory. They reflected not just present conditions, but the cumulative effect of past climates. This slow response created a world where cause and effect was separated by time. The Ice Age was not simply cold because it was cold. It was cold because the system had been cold long enough for ice to accumulate, spread, and reinforce itself. Once established, ice sheets altered atmospheric circulation, redirected storms, and influenced ocean currents. These changes helped maintain the conditions that favored ice. The edges of glaciers were especially dynamic places. At the margins, ice met land, water, and air in complex ways. During summer, meltwater streams ran across ice surfaces, carving channels that glistened briefly before freezing again. At the terminus, ice melted directly into rivers or lakes, feeding cold, sediment water into surrounding landscapes. In some areas, ice ended in the ocean, breaking off into icebergs that drifted away, carrying fresh water far from its source. Each of these processes contributed to the glacier's breathing. Growth was not just about snow falling. It was about ice flowing inward and outward, adjusting its shape and thickness in response to forces acting upon it. Shrinkage was not just about melting. It was about ice thinning, fracturing, and losing contact with the ground. What made the late Ice Age particularly significant was that the breathing of glaciers began to change character. The inhalations grew slightly weaker, the exhalations slightly stronger. Summers became just warm enough, just often enough to allow meltwater to persist longer. Snow lines crept upward. Accumulation zones shrank, while ablation zones expanded. This shift did not announce itself with drama. There were no sudden collapses at first. Instead, ice margins retreated unevenly. Some regions thinned rapidly, while others remained stubbornly frozen. Ice sheets became more fragmented. Their edges scalloped by, melting and flow rather than advancing smoothly. Internal stresses increased as ice redistributed itself in response to thinning and sliding. As ice thinned, pressure at the base decreased in some areas, reducing basal melting and slowing flow. In others, meltwater increased, accelerating movement. The system grew more heterogeneous, less predictable. This variability mattered because it created weak points. Areas where ice was already thinner or more fractured were more vulnerable to sudden changes. One of the most consequential outcomes of this evolving glacial behavior was the formation of large meltwater reservoirs. As glaciers retreated unevenly, they blocked valleys and drainage routes, trapping water behind ice dams. These lakes did not form because glaciers were dying. They formed because glaciers were still present, still powerful enough to obstruct water, but no longer cold or thick enough to remain perfectly stable. The slow breathing of glaciers thus set the stage for something much faster. Ice had accumulated over tens of thousands of years. It had shaped continents with patience. But water, once freed from ice, behaved differently. It moved quickly. It responded immediately to gravity. And when trapped in large volumes, it exerted forces that ice could resist only temporarily. Even before catastrophic releases occurred, the presence of large meltwater lakes altered glacial behavior. Water pressing against ice dams increased stress. Water seeping beneath ice reduced friction. Seasonal fluctuations in lake levels added cycles of loading and unloading that fatigued the ice over time. Each summer melt became not just a release of water, but a test of the dam's strength. All of this was happening while the planet as a whole continued its gradual warming. Orbital conditions continued to favor increased summer sunlight in the northern hemisphere. Greenhouse gas levels slowly rose, influenced by changes in vegetation, oceans, and biological activity. The system was being nudged year after year in the same direction. From a distance, glaciers still dominated the landscape. Ice sheets still covered vast areas, but internally they were adjusting, reorganizing, and in some places weakening. The breathing of glaciers had become uneven, marked by deeper exhales and shallower inhales. This matters because glaciers are not passive responders to climate. They are active agents within it. Their movement redistributes mass. Their meltwater alters landscapes and ocean chemistry. Their presence influences weather patterns. When their behavior changes, the effects ripple outward. As glaciers began to lose their grip, they did not simply retreat quietly. They interacted with water in increasingly complex ways. Meltwater that once drained away, harmlessly now pulled behind ice barriers. Ice that once flowed steadily, now stalled in some places and surged in others. The slow breathing that defined the Ice Age began to interact with faster processes that ice alone could not control. In this sense, the glaciers of the late Ice Age were caught between worlds. They were still creatures of cold, built by long winters and preserved by weak summers. But they were also becoming participants in a warmer system, one where liquid water played a growing role. Their movements reflected this tension, slow overall, but increasingly punctuated by moments of instability. The glaciers continue their measured motion. They creep, slide, fracture, and heal. They inhale winter snow and exhale summer melt. To the untrained eye, the world still looks locked in ice. But beneath that appearance, the rhythm has changed, and the next breath will not be like the last. When so much of Earth's water is locked away on land as ice, the oceans cannot help but respond. They shrink, not by drying up, but by retreating. During the height of the last ice age, global sea levels were dramatically lower than they are today. Lowered not by a few meters, but by more than 100. This change did not happen overnight, and it did not happen evenly, but its consequences reshaped the planet in ways that quietly influenced climate, ecosystems, and the paths taken by both animals and humans. With sea levels drawn down, coastlines moved outward, sometimes by dozens or even hundreds of kilometers. Continental shelves, which today lie submerged beneath shallow seas, were exposed as wide, gently sloping plains. These newly revealed lands were not uniform beaches or featureless mud flats. They were complex environments shaped by rivers, winds, seasonal freezes, and sparse vegetation. In some regions, they supported grasslands and shrublands. In others, they remained cold, dry, and windswept, more like polar deserts than fertile ground. The oceans themselves grew smaller in surface area, but their influence reached farther inland. Rivers extended their courses across exposed shelves, cutting deep channels as they adjusted to lower base levels. Where a river once emptied into a nearby sea, it now traveled much farther, carving valleys that would later be drowned when sea levels rose again. Many of the submarine canyons visible along modern continental margins were shaped or deepened. During this time, when rivers flowed directly across land that no longer exists above water, lower seas also meant stronger contrast between land and ocean climates. The vast, shallow coastal waters that today moderate temperatures and generate moisture were reduced. With less ocean surface close to land, coastal regions experienced colder, drier conditions. Winds blowing off large ice sheets carried cold air across exposed plains, reinforcing the chill far beyond the ice margins themselves. Shadows, both literal and climatic, stretched across the landscape. The phrase, long shadows, fits not only because of the low-angle sunlight common to high latitudes during the Ice Age, but also because ice sheets cast metaphorical shadows over the entire climate system. Massive walls of ice influenced atmospheric circulation. They redirected winds, altered storm tracks, and shaped precipitation patterns. Regions downwind of ice sheets often became dry as cold air held little moisture. Snow fell where conditions allowed, but rain was scarce. In many places, dust became a dominant feature of the environment. Dust might seem like a minor detail, but it played an important role. Fine particles lifted by strong winds settled across ice sheets and exposed plains alike. On ice, this dust darkened the surface, allowing it to absorb slightly more sunlight during summer months. The effect was subtle but persistent. On land, dust enriched some soils while stripping others, contributing to a patchwork of fertility and barrenness that shaped plant growth and animal movement. Lower sea levels also created connections that no longer exist. Land bridges emerged where shallow seas had once separated continents. The most famous of these connected Asia and North America across what is now the Bering Strait. This land bridge, known as Beringia, was not a narrow corridor, but a broad region that supported grasses, shrubs, and large grazing animals. It was cold, but relatively dry, and it provided a route for species to move between continents over thousands of years. Humans use these connections too, though not necessarily as a single, dramatic migration. Movement across land bridges likely happened gradually over many generations, following animals and seasonal resources. The lowered seas made the world feel larger and more continuous. Even as ice sheets blocked other routes, geography became a shifting puzzle, opening some paths while closing others. The reduced volume of the oceans affected their chemistry as well. With more fresh water locked in ice, seawater became slightly saltier. This change influenced ocean density and circulation. The formation of deep water, driven by cold, salty water sinking at high latitudes, behaved differently under Ice Age conditions. Ocean currents adjusted, redistributing heat in new patterns that fed back into the climate system. At the same time, colder global temperatures meant that sea ice expanded. In polar regions, ice covered larger portions of the ocean for longer periods each year. Sea ice acts as an insulating layer, reducing the exchange of heat between ocean and atmosphere. It also reflects sunlight, reinforcing cooling. With more sea ice present, especially in the northern hemisphere, seasonal cycles became sharper. Summers struggled to erase winter's imprint. Despite this cold dominance, the oceans were not lifeless or static. Marine ecosystems adapted to the changing conditions. Productivity shifted with nutrient availability and ice cover. Some species thrived in cold, nutrient-rich waters, while others retreated or disappeared. The lowered seas altered coastal habitats, removing shallow environments that many species rely on while expanding others elsewhere. On land, the exposed continental shelves became part of the ecological system. Animals grazed and migrated across these areas, unaware that they were temporary. Plants colonized where they could, constrained by cold wind and limited moisture. Permafrost extended across large regions, locking water into frozen ground and limiting drainage. During brief summers, the surface thawed just enough to allow plant growth before freezing again. These conditions created long-term stability mixed with seasonal hardship. Life learned to operate within narrow windows. Growth happened quickly when temperatures allowed. Migration followed predictable patterns shaped by geography that would later vanish. This predictability, however, was built on a fragile foundation. As the climate slowly warmed, the lowered seas became a reservoir of potential change. Ice sheets thinning on land did not immediately translate into rising oceans. Meltwater often pulled in lakes or flowed into rivers that drained into enclosed basins or cold oceans where ice persisted. Sea levels responded unevenly, lagging behind ice loss in some periods and accelerating in others. The exposed shelves also influenced how future floods would behave. When large volumes of meltwater were suddenly released from ice-dammed lakes, they often flowed across these low-lying areas. Following river valleys carved during the low sea phase, the shape of the land guided water with efficiency. Channels cut deep into exposed shelves would later become pathways for rising seas, allowing ocean water to surge inland more easily when levels rose. Another subtle effect of lower seas was the way sunlight interacted with Earth. With more land exposed at high latitudes, especially pale, dusty plains, the planet's reflectivity changed. Some areas reflected more sunlight than the dark ocean waters they replaced, reinforcing cooling. Others, darker with vegetation or sediment, absorbed more heat locally. These competing effects added complexity to the climate response, smoothing some transitions and sharpening others. Lower seas also meant that the planet's gravitational balance shifted slightly. Large ice sheets exerted their own gravitational pull, drawing ocean water toward them. When ice was extensive, sea levels near ice sheets could be locally higher than farther away, even while global levels were lower overall. This uneven distribution meant that, as ice melted, sea level rise would not be uniform. Some regions would experience rapid inundation, while others lagged behind. For human populations living near coasts, this created a world where the sea was both distant and influential. Shorelines lay far away, but rivers connected inland regions to the ocean's rhythms. Marine resources were less accessible in some areas, while inland resources expanded across exposed plains. The memory of the sea passed through stories, and seasonal movements became part of cultural awareness long before coastlines returned. The long shadows of the Ice Age stretched not only across space, but across time. The landscapes shaped during this period would influence how water moved when the ice finally loosened its grip. Valleys carved by rivers on exposed shelves would guide floodwaters. Depressions formed by crustal sinking under ice would become basins for lakes. The configuration of land and sea at low levels set the stage for everything that followed. As warming progressed, the relationship between ice, land, and ocean grew more unstable. Ice sheets continued to thin and retreat, but unevenly. Some areas lost ice quickly, releasing water toward the oceans. Others remained frozen, holding back meltwater behind ice barriers. Sea levels began to rise in steps rather than a smooth curve, responding to pulses of water delivered by sudden events rather than steady melting alone. From the perspective of the planet, this was a transitional phase neither fully glacial nor fully interglacial. Ice still dominated high latitudes. Seas were still far from their modern positions. Yet the system was no longer in balance. The long shadows cast by ice began to shorten, not uniformly, but in fits and starts. The exposed lands that once seemed permanent started to feel provisional. Rivers deepened their channels, responding to increased meltwater. Lakes expanded and contracted seasonally with greater amplitude. Ice margins grew more irregular. All the while, the oceans waited, vast and patient, ready to receive what the ice would eventually give back. This waiting matters because the oceans are not passive recipients. They respond to freshwater influx with changes in circulation, temperature distribution, and sea ice formation. When large volumes of cold, fresh water enter the ocean suddenly, they can disrupt currents that transport heat across the globe. These disruptions can produce abrupt climate shifts, cooling some regions, even as the long-term trend remains toward warming. The world of lower seas was therefore not just a background condition of the Ice Age. It was an active participant in the planet's slow transformation. It shaped pathways, stored potential energy, and created conditions where sudden change could ripple far beyond its point of origin. Beneath the surface of the great ice sheets, far from the wind-cored plains and frozen horizons, a quieter but far more consequential story was unfolding. From above, The ice appeared solid, inert, and unyielding. It stretched across continents with a confidence that suggested permanence. Yet below that frozen exterior, forces were building that would eventually overwhelm even the thickest walls of ice. This tension was not obvious, not dramatic, and not sudden. It accumulated slowly, layer by layer, season by season, hidden from view and easy to underestimate. To understand this hidden tension, it helps to imagine the base of an ice sheet, not as a clean boundary between ice and rock, but as a complex shifting interface. The immense weight of ice pressed down the land with pressure so great that they altered the physical behavior of both materials. Rock fractured, sediments compacted, and ice at the base approached its melting point. Even in a world dominated by cold, pressure alone can lower the melting temperature of ice. And where pressure was highest, particularly beneath the thick central regions of ice sheets, melting could occur despite freezing surface conditions. This basal melting produced thin films of water between ice and bedrock. In some places, the water existed as a continuous layer. In others, it flowed through networks of channels and cavities carved into the ice and the underlying sediment. The presence of this water fundamentally changed how ice behaved. Ice frozen directly to bedrock resists movement. Ice separated from rock by water slides. Even a small amount of lubrication could allow vast masses of ice to shift more easily, redistributing pressure and altering flow patterns across entire regions. The water beneath the ice did not come from a single source. Some of it was generated by pressure-induced melting at the base. Some descended from the surface, especially during warmer summers when melt water found its way downward through cracks, crevices, and vertical shafts known as moulins. These pathways allowed surface water to bypass the cold upper layers of ice and reach the base rapidly, sometimes within hours. When this happened, the basal system could change abruptly, transitioning from relatively dry and resistant to wet and mobile. This interplay between surface melting and basal lubrication created a feedback loop. Increased melting led to faster ice flow, which transported ice toward lower elevations where temperatures were warmer, increasing melting further. Yet, this acceleration was not uniform. Ice sheets are not smooth domes. They're shaped by bedrock topography, internal structure, and historical patterns of flow. Some areas responded quickly to added water, surging forward in bursts. Others remained sluggish, anchored by rough terrain or frozen sediments. Over time, this uneven response created stress within the ice itself. Ice is strong in compression, but weak in tension. As different parts of an ice sheet moved at different speeds, cracks formed. Casses opened where ice was stretched, especially near the margins and over uneven ground. While most crevasses remained shallow, some penetrated deeply enough to serve as conduits for surface water, linking the upper and lower parts of the ice sheet more directly. Meanwhile, the land beneath the ice was undergoing its own transformation. The weight of ice depressed the crust, pushing it downward by hundreds of meters in some regions. This subsidence altered drainage patterns, creating low areas where water naturally collected. As ice margins fluctuated, these depressed basins became ideal locations for meltwater to pool. Ice did not need to retreat entirely to allow lakes to form. It only needed to block existing drainage routes while meltwater supply increased. Sediments beneath the ice added another layer of complexity. In many regions, Glaciers rested not on solid bedrock, but on thick layers of unconsolidated sediment left behind by previous glacial advances. These sediments could deform under pressure, behaving more like a thick paste than solid ground. When saturated with water, they became even more mobile, allowing ice to slide more easily. This sediment deformation further reduced resistance to flow, amplifying the effects of basal water. All of these processes were sensitive to small changes. A slightly warmer summer could increase surface melting just enough to send additional water to the base. A modest thinning of ice could reduce pressure in one area while increasing stress in another. A minor shift in ice flow could reroute water beneath the ice, focusing it into channels that eroded and expanded with each passing season. None of these changes alone would have been catastrophic. Together, they created a system increasingly prone to instability. One of the most significant consequences of this hidden tension was the formation of ice dams. As glaciers flowed across valleys and lowlands, they blocked natural drainage routes. Rivers that once carried meltwater to the sea were diverted or stopped entirely. Water backed up against the ice, forming lakes that grew larger with each melt season. These lakes were not gentle features. They pressed against the ice with tremendous force, exploiting fractures and weaknesses created by internal stress and basal lubrication. The ice dams themselves were dynamic. They thickened as ice flowed into them and thinned as melting and deformation took their toll. The pressure exerted by water behind a dam increased with depth, and as lakes grew, that pressure climbed. Water is relentless. It seeks the lowest point, the smallest crack, the weakest bond. Once it finds a path, it enlarges it rapidly. A trickle becomes a torrent. A stable barrier becomes a failing one. Importantly, this tension did not build in isolation from the broader climate system. As the planet continued its gradual warming, the balance between accumulation and melting shifted. Snowfall patterns changed. Some regions received less snow, even as temperatures rose, reducing the supply of new ice to replace what was lost. Other areas experienced increased precipitation. But in warmer conditions, more of that precipitation fell as rain rather than snow, contributing directly to meltwater rather than ice growth. The timing of melting also mattered. Warmer summers extended the melt season, allowing water to accumulate for longer periods. Instead of brief pulses that froze again quickly, meltwater persisted, flowing and pooling in ways that stressed the ice more effectively. Each year the system was tested, and each year the margin of safety narrowed. From above, the ice still appeared vast and dominant. From below, it was under strain. The tension was not just mechanical, but temporal. Ice had accumulated over tens of thousands of years, storing water in frozen form. The processes that released that water operated on much shorter time scales. This mismatch between slow storage and fast release meant that when release occurred, it could be sudden and overwhelming. It is also worth considering how silent this tension was. There were no warning signs obvious to anyone living nearby. No gradual rise in river levels that could be traced back to a specific source. No visible cracking across the ice sheet that announced impending failure. The system failed internally, out of sight, guided by physics rather than perception. This hidden buildup helps explain why the floods that followed were so extraordinary. They were not the result of a single warm year or an isolated event. They were the culmination of thousands of years of slow change, stored energy, and accumulating water. The ice had become a barrier holding back forces it could no longer fully contain. As ice sheets thinned and retreated unevenly, the number and size of meltwater lakes increased. Some drained gradually through subglacial channels, releasing water in manageable amounts. Others remained trapped, growing deeper and more unstable. The difference between these outcomes often came down to small variations in ice thickness, bedrock shape, or water rooting beneath the ice. This variability is crucial. It means that the end of the Ice Age was not uniform. Some regions experienced relatively gentle transitions, with ice retreating and meltwater dispersing over long periods. Other regions were subjected to repeated catastrophic floods that transformed landscapes almost overnight. Both outcomes emerge from the same underlying processes shaped by local conditions. The hidden tension beneath the ice also influenced how quickly ice sheets could respond to future warming. Once basal systems were established, ice could accelerate rapidly when conditions allowed. This responsiveness meant that ice sheets were no longer just passive indicators of climate change. They became active contributors, capable of amplifying and redistributing its effects. As this tension continued to build, the system edged closer to thresholds that once crossed could not be easily reversed. Ice dams weakened, meltwater volumes increased, basal lubrication spread. The internal structure of ice sheets grew more fractured and stressed. The balance that had sustained the Ice Age for so long was no longer stable. Yet even at this stage, the world above remained cold by modern standards. Ice still covered vast areas. Sea levels were still low. To an observer without knowledge of what lay beneath the ice, the planet might have seemed unchanged. This disconnect between appearance and reality is one of the defining features of the Ice Age's final phase. For most of the Ice Age, ice behaved as if it were certain of itself. It accumulated, thickened, and spread with a kind of quiet confidence, responding predictably to cold and snowfall. Even when it flowed, it did so in ways that were slow, restrained, and largely self-limiting. But as the climate continued its gradual shift, there came a point where ice no longer behaved as it once had. Not because it suddenly became fragile, but because the conditions that supported its strength were slipping away. This was the moment when ice began to forget what had held it together. Forgetting strength does not mean losing mass overnight. Ice sheets did not vanish suddenly or melt evenly across their surfaces. Instead, they became inconsistent. Their responses to temperature, pressure, and water changed. The same amount of warmth that once produced little effect now triggered noticeable thinning. The same snowfall that once sustained growth now failed to compensate for losses elsewhere. Strength in this context was not just thickness. It was coherence, resistance, and the ability to recover after stress. One of the earliest signs of this change was a subtle shift in the seasonal balance. During the coldest phases of the Ice Age, winter snowfall reliably outweighed summer melting across most of the ice sheets. Snow accumulated in the interior faster than it could be lost at the margins. As orbital conditions changed and summers grew slightly warmer, that balance tipped. The melt season lengthened. Snow lines crept upward. Areas that once added mass year after year began to break even, then slowly lose ice. This shift did not occur everywhere at once. Some regions, especially high central domes of ice sheets, remained cold enough to sustain accumulation for a long time. Marginal zones, however, felt the change first. These edges are where ice is thinnest, where elevations are lower, and where temperatures hover closest to the melting point. Here, even small increases in summer warmth had outsized effects. Surface melting increased, but more importantly, it persisted. Water no longer refroze quickly at the end of each warm day. Instead, it lingered, pooling in shallow depressions on the ice surface. These pools absorbed sunlight more efficiently than bright snow, warming further and deepening. Water found weaknesses in the ice, draining downward through cracks and crevasses that widened with repeated use. Once meltwater reached the interior of the ice sheet, its influence multiplied. Water transported heat downward, warming ice that had long remained insulated from surface conditions. At the base, additional water increased lubrication, allowing ice to slide more easily over bedrock and sediment. This sliding did not simply move ice out of the way. It altered stress patterns within the ice, stretching it in some places and compressing it in others. Ice is strong when its internal structure is intact. Crystals interlock. Layers support one another. But when stress becomes uneven, that structure begins to degrade. Cases form not just at the surface, but internally. Zones of weakness propagate through the ice, reducing its ability to respond elastically to pressure. Once fractured, ice does not heal quickly, especially in warmer conditions. At the same time, thinning ice exerted less pressure on the ground beneath it. This reduced pressure had mixed effects. In some areas, less pressure meant less basal melting, which could temporarily slowing. In others, it allowed water to move more freely beneath the ice, reorganizing subglacial drainage systems. Water that once spread out thinly could become focused into channels, increasing erosion and further weakening icid contact. The land beneath the ice also began to respond differently. As ice thinned and retreated, the crust slowly rebounded upward, a process known as isoadic adjustment. This uplift was gradual, but it altered slopes and drainage routes. Water that once flowed away from ice margins might now be trapped, pooling against retreating ice fronts. The geometry of the landscape was changing beneath the ice's feet, so to speak, making old patterns of stability unreliable. Another important factor was the changing nature of precipitation. As temperatures rose, a greater fraction of precipitation fell as rain rather than snow, especially near ice margins. Rain does not build ice, it erodes it. Rainwater delivers heat directly to the surface, accelerates melting, and runs off quickly, often carrying debris that darkens ice downstream. Each rain event acted as a localized stress test, challenging ice that had evolved under colder snow-dominated conditions. Wind patterns shifted as well. With less ice covering some regions and more open water elsewhere, atmospheric circulation adjusted. In some areas, this brought warmer air inland more frequently. In others, it altered snowfall distribution, starving certain parts of ice sheets of the accumulation they needed to remain stable. Ice does not respond well to uneven feeding. When supply becomes patchy, internal stresses increase. Over time, these factors combined to produce ice sheets that were still massive, still dominant, but less resilient. They could no longer absorb disturbances as effectively. Where once a warm decade might have passed with little long-term effect, now it left a mark. Thinning accumulated, fractures persisted. water pathways remained open longer each year. This loss of resilience mattered because ice sheets exist close to thresholds. There are conditions under which they grow, conditions under which they shrink, and narrow zones in between, where small changes can push them one way or the other. As the climate warmed, ice sheets moved into these threshold zones. They did not collapse immediately, but they became sensitive. Sensitivity is dangerous for large systems. It means response times shorten, feedback loops strengthen, variability increases. Ice began to behave less like a slow buffering component of the climate system and more like an active, reactive one. Surges became more common. Retreats accelerated in some sectors, while others lagged behind. The overall shape of ice sheets grew irregular, with lows extending into lowlands and thinner regions pulling back. Crucially, this regular retreat favored the formation of unstable configurations. Ice tongues advanced across valleys and blocked drainage routes, even as surrounding areas thinned. These tongues were often underlaying by water-saturated sediments, making them prone to sudden movement or failure. Behind them, meltwater accumulated in growing lakes, pressing against ice that was no longer as strong as it once had been. The phrase "forgetting its strength" captures this gradual loss of integrity. Ice did not suddenly become weak in an absolute sense. It remained thick, cold, and powerful in many places. But it no longer remembered how to behave as a single coherent system. Different parts responded differently. Old balances no longer applied. Past performance was no guarantee of future stability. From a distance, this change was invisible. Ice sheets still covered continents. Glaciers still advanced and retreated seasonally. To early humans living nearby, the world remained cold, demanding, and familiar. But the rules governing ice had shifted. The margin for error had narrowed. This shift also altered how ice interacted with water. In earlier phases of the Ice Age, meltwater produced during summer was often limited and efficiently refrozen or drained. Now meltwater volumes increased, and drainage pathways struggled to keep up. Lakes grew larger and persisted longer. Seasonal cycles of filling and partial draining fatigued ice dams, weakening them year after year. Water pressure became a dominant force. As lakes deepened, pressure at their bases increased, sometimes exceeding the strength of ice, holding them back. Water forced its way into cracks, lifting ice slightly and reducing friction. Once water began to flow beneath an ice dam, erosion accelerated rapidly. Channels widened, flow increased. Ice that had once resisted now yielded. These processes did not occur in isolation. They interacted with broader climate variability. Periods of rapid warming, even if brief, could trigger outsized responses from ice already near its limits. Conversely, short-lived cooling events might slow retreat temporarily, but could not restore lost strength. Once coherence was gone, rebuilding it required conditions that no longer existed. In this way, the Ice Age entered a new phase. It was no longer defined solely by accumulation and slow flow, but by instability and transition. Ice still mattered, but it mattered differently. It became both a remnant of the cold past and a source of rapid change. This matters for understanding what came next, because the great floods associated with the end of the Ice Age were not anomalies. They were expressions of a system that had lost its ability to release energy slowly. Ice had stored water for tens of thousands of years. Now weakened and fragmented, it could not always control how that water returned to the rest of the planet. As ice forgot its strength, water remembered gravity. It waited patiently behind thinning barriers, responding instantly when given a path. The contrast between the slow forgetting of ice and the sudden decisiveness of water defines the transition we are approaching. There is no single calendar date that marks the moment when ice failed. No universal hour when glaciers everywhere gave way at once. Instead, there were days scattered across regions and separated by years or centuries when something crossed a line. On those days, the balance that had held for so long finally broke. Ice that had resisted pressure, weight, and time itself could no longer do so. Water moved from being contained to being released. And once that transition began, it did not proceed gently. To understand how such a day could arrive, it helps to remember that ice dams are not engineered structures. They are not designed with margins of safety or reinforced against failure. They are temporary outcomes of flow and blockage, formed because ice happens to be in the way. As glaciers advanced and retreated unevenly, they blocked valleys, river outlets, and lowlands that once allowed water to escape freely. Behind these blockages, water accumulated season after season, rising slowly, quietly, invisibly dangerous. At first, the water behaved. It filled basins spread out and pressed against the ice with steady force. The ice responded by deforming slightly, adjusting its shape under pressure. For long stretches of time, this equilibrium held. The lake might grow deeper, but the dam thickened as ice flowed into it from upstream. Cracks opened, but refroze. Small leaks developed, but drained enough water to relieve pressure temporarily. What made the eventual failure inevitable was not the size of the lake alone, but the changing nature of the ice holding it back. As ice thinned and warmed, it became more permeable. Casas penetrated deeper. Surface melt water reached internal fractures more frequently. Basal lubrication increased. The dam was no longer a single solid mass, but a stressed, layered structure riddled with weaknesses. Water exploits weakness with efficiency. It does not need a large opening. It needs a floor, a narrow crack that reaches deep enough, a seam where ice crystals no longer interlock tightly, a zone where pressure and temperature combine to keep water liquid. Once water begins to move through such a floor, it changes the conditions around it immediately. Flowing water transfers heat. Heat melts more ice. Melting enlarges the passage. Enlarged passages allow more water to flow. This is a runaway process, and it can accelerate with startling speed. On the day the ice could no longer hold, the process likely began quietly. Perhaps a trickle formed beneath the dam, unnoticed on the surface. Perhaps a subglacial channel that had carried small seasonal flows suddenly widened beyond recovery. At first, the lake level may have dropped only slightly, but as flow increased, the drop accelerated. Pressure that had been distributed across the dam became focused along specific paths, carving them open. Once the flow reached a critical threshold, the dam's fate was sealed. Ice doesn't fail like concrete, snapping suddenly along a clean break. It deforms, fractures, and tears. Large sections can lift, float, or collapse inward as water undermines their support. In some cases, the dam may have failed catastrophically, releasing a wall of water within hours. In others, the failure unfolded over days, with discharge increasing continuously until the lake was largely emptied. The scale of these releases is difficult to convey, in familiar terms. These were not floods in the sense of swollen rivers spilling over their banks. They were megafloods, involving volumes of water comparable to inland seas. Water surged out at speeds that rivaled or exceeded modern flood events by orders of magnitude. The flow carried icebergs torn from the dam itself, along with rock, sediment, and debris scoured from the land. As the water rushed downstream, it followed paths dictated by topography that had been shaped during the long period of low sea levels. Valleys were deep and steep. Channels were direct. There were few obstacles to slow the flow. In many places, the water spread across wide areas, forming temporary inland seas before finding new outlets and accelerating again. The energy involved in such floods was immense. Water, moving at high speed, exerts tremendous force. It can lift and transport boulders the size of houses. It can strip soil down to bedrock. It can carve channels hundreds of meters wide and tens of meters deep in a matter of days. Features that would normally require thousands of years of river erosion formed almost instantly. The land did not respond gradually. It yielded. Hills were truncated. Ridges were sliced through. Rock surfaces were polished and grooved by sediment-laden flow. In some regions, the floodwaters left behind streamlined hills, known as drumlins or flood bars, shaped not by ice but by water, behaving like a fluid bulldozer. As the floodwaters raced onward, they did not simply drain away harmlessly. They entered river systems, lakes, and eventually oceans, delivering massive pulses of fresh water. These pulses altered water chemistry, temperature, and circulation far beyond the flood's point of origin. In some cases, they disrupted ocean currents that depended on a delicate balance of salt and heat, triggering short-term climate reversals, even as the long-term trend toward warming continued. The immediate aftermath of such a flood would have been a transformed landscape. Where there had been lakes, there were empty basins, scattered with stranded ice blocks that melted slowly over years. Where there had been rivers, there were oversized channels, far larger than any flow that would later occupy them. Vegetation was stripped away, soils were redistributed, ecosystems were reset. Importantly, these events were not singular. In many regions, the same ice dam reformed after failure. As ice continued to flow into the blocked valley, it rebuilt the barrier. Melt water continued to accumulate. Pressure built again, and eventually, the process repeated. Some areas experienced dozens of such floods over a few thousand years, each one reshaping the land further, each one delivering another pulse of water to downstream systems. This repetition matters because it means the end of the Ice Age was not a single release, but a sequence of them. Each flood removed ice mass and transferred water from land to sea. Each flood lowered the elevation of ice dams and made future failures more likely. The system stepped downward, not smoothly, but in jolts. For any humans living nearby, these days would have been unforgettable. Even if no one witnessed the exact moment of failure, the aftermath would have been obvious. Rivers that once flowed gently would have become torrents. Familiar routes would have vanished. The sound alone would have been overwhelming, a continuous roar echoing across valleys. Such experiences, rare but immense, would naturally become embedded in memory and retold across generations. Yet, from the perspective of the planet these days, were simply efficient mechanisms. Ice had stored water too long and too thoroughly. Gradual melting alone could not return it to the oceans fast enough to maintain equilibrium. Floods accomplished in days what slow melt would have taken centuries to achieve. It is tempting to think of these events as disasters in a modern sense, but in the language of Earth systems, they were adjustments, violent, yes, but also functional. They relieved pressure. They redistributed mass. They accelerated a transition that was already underway. Without them, the Ice Age might have lingered longer. Its retreat stretched thin across time. The phrase, "the day the ice could no longer hold," captures a moment of inevitability rather than surprise. By the time failure occurred, the conditions for it had been building for thousands of years. The ice did not fail because of a single warm summer or an unlucky fracture. It failed because it had become a barrier in a system that now favored flow. Once water had escaped, the ice sheet was changed permanently. The loss of mass reduced pressure upstream. Flow patterns shifted. The dam might reform, but it would rarely be as strong as before. Each failure weakened the memory of stability further. As these events repeated across different regions, their cumulative effect grew. Sea levels rose in steps. Landscapes were reworked at continental scales. Ocean circulation experienced repeated shocks. The climate system oscillated as it absorbed and responded to these disruptions. What matters most is that these floods were not side effects of deglaciation. They were central to it. They represent the moment when ice stopped controlling water and water began controlling ice. Once that reversal occurred, the Ice Age's dominance was effectively over, even if ice itself persisted for millennia afterward. Long before any flood tore across the land, before valleys were scoured bare and rivers were remade in moments, the water that would drive those changes was already present. It did not rush. It did not surge. It waited patiently, quietly, and in volumes so large that even the ice restraining it was gradually shaped by its presence. This waiting water gathered in a place that at first glance might have seemed unremarkable, a broad basin bordered by mountains and ice, filling slowly under a cold sky. This was Lake Missoula, one of the largest glacial lakes ever to exist, and one of the clearest examples of how the end of the Ice Age was prepared long before it was revealed. The basin that would hold Lake Missoula lay in what is now western Montana. Its shape was not accidental. It was the result of ancient tectonic forces, erosion, and long-term river activity that predated the Ice Age itself. Valleys had been carved over millions of years, leaving behind a landscape capable of holding vast quantities of water if drainage were ever blocked. During most of Earth's recent history, rivers flowed freely through this region, carrying meltwater and rain toward the Pacific. But during the Ice Age, that freedom disappeared. As the Cordilleran ice sheet expanded southward from what is now Canada, one of its lobes advanced into the northern Rocky Mountains. This ice did not simply drape over the land. It flowed into valleys, thickened, and pressed forward until it crossed a critical point. Eventually, it blocked the Clark Fork River, the primary drainage route out of the basin. With that blockage in place, water had nowhere to go. At first, the accumulation was modest. Seasonal meltwater and precipitation collected behind the ice dam, forming a growing lake. Year after year, the lake expanded, spreading outward across the basin, rising steadily as long as inflow exceeded outflow. The surrounding climate was still cold by modern standards, but summers were warm enough to generate meltwater from nearby glaciers and snowfields. Each melt season added to the lake's volume. Over time, Lake Missoula grew to staggering proportions. At its maximum extent, it covered an area of several thousand square km and reached depths of more than 600 meters in places. To put that into perspective, the water level rose high enough to leave visible shorelines etched into mountain slopes far above the modern valley floor. These shorelines, preserved as parallel terraces, are still visible today, silent markers of a waterline that once stood hundreds of meters above the present landscape. The water filling Lake Missoula was cold, dense, and heavily laden with sediment. Rivers entering the lake carried fine particles ground from bedrock by glaciers upstream. As these rivers entered the still water of the lake, sediment settled out, forming layered deposits on the lake floor. Over time, these layers built up, recording seasonal variations in inflow, much like tree rings, record years. Each layer represented a quiet interval, another season of waiting. The ice dam that restrained the lake was immense. It was not a thin wall of ice perched precariously across a valley. It was a massive lobe of the Cordillera, an ice sheet several hundred meters thick, grounded against bedrock and sediment. At first, it was strong enough to resist the pressure of the growing lake. Ice flowed into the dam from upstream, thickening it even as water pressed against it from behind. But strength does not mean invulnerability. As Lake Missoula deepened, the pressure at its base increased. Water pressure rises with depth, and at the bottom of the lake, that pressure was enormous. The ice dam was subjected not just to the weight of the ice itself, but to the relentless force of the water pushing against it. Over time, this pressure exploited every weakness. One of the most important features of this system was that the ice dam was not frozen solid to the ground along its entire base. In places, basal melting occurred due to pressure and geothermal heat from the earth below. Meltwater beneath the ice reduced friction, allowing the dam to deform and shift slightly. These movements were slow, but they mattered. They opened pathways, closed others, and constantly changed the internal structure of the ice. Meanwhile, surface melting played its role. During warmer summers, meltwater formed on the surface of the ice dam and surrounding glaciers. Some of this water drained away harmlessly. Some of it found cracks and shafts plunging downward into the interior of the ice. When surface water reaches the base of a glacier, it can dramatically alter conditions, increasing lubrication and flow. At Lake Missoula, this meant the water from above and water from behind were both interacting with the ice dam in complex ways. Despite all this, the lake remained contained for long periods. This is one of the most striking aspects of Lake Missoula's story. The system did not fail immediately or constantly. It held sometimes for decades or centuries at a time. During these intervals, the landscape around the lake settled into a strange stability. Shorelines formed and persisted. Sediments accumulated quietly. Ecosystems adapted to the presence of a vast inland sea. For any humans living within reach of this region, Lake Missoula would have been a dominant feature of the world. It would have altered local climate, moderating temperatures near its shores and influencing wind patterns. It would have provided water and resources, but also imposed barriers. The lake was not static, but its changes were slow enough to feel predictable within a lifetime. What made Lake Missoula different from ordinary lakes was not just its size, but its dependence on ice for containment. Unlike lakes held back by rock or sediment, this lake existed only as long as the ice dam remained intact. Its stability was therefore tied directly to the condition of the ice sheet, which, as we've seen, was becoming less reliable over time. As the climate continued to warm, subtle changes accumulated. Summers grew long enough to deliver more meltwater into the basin. Snowfall patterns shifted, affecting how much new ice replenished the dam. The ice lowing the Clark Fork River thinned slightly, then recovered, then thinned again. Each cycle left it a little more fractured, a little more stressed. The water in Lake Missoula responded to these changes by rising and falling, but the overall trend was upward. Each year that inflow exceeded leakage, the lake deepened. Pressure at the base increased. The equilibrium became more precarious. The water waited, not passively, but with stored energy. What is remarkable is how long this waiting could continue. Ice dams can be surprisingly resilient even under extreme pressure. As long as leakage paths remain small and manageable, the system could persist. Minor releases may have occurred, draining some water subglacially, without catastrophic failure. These releases would have lowered the lake level temporarily, relieving pressure only for the lake to refill in subsequent years. This cycle of filling, partial draining, and refilling likely happened multiple times. Each cycle weakened the ice further. Subglacial channels carved by flowing water grew larger and more efficient. Ice that had once sealed cracks effectively became less able to do so as temperatures rose and internal structure degraded. At some point, the system crossed a threshold. The precise trigger may have varied from one flood to the next. In some cases, rising water pressure may have lifted the ice dam slightly, allowing water to rush beneath it. In others, surface melt water may have punched through to the base, initiating rapid flow. Once flow began in earnest, it was self-reinforcing. When Lake Missoula finally drained, it did so with extraordinary speed. Water volumes equivalent to some of the largest modern lakes were released over days or even hours. But this was not a one-time event. After each drainage, the ice dam reformed as ice continued to flow into the valley. Meltwater once again accumulated. The lake returned. The water waited again. Evidence suggests that this cycle repeated dozens of times over several thousand years. Each time, the flood waters carved deeper into the landscape downstream. Each time, the lake refilled, sometimes reaching similar levels, sometimes slightly lower or higher, depending on conditions. The repetition amplified the impact, transforming vast regions of the Pacific Northwest. The waiting water of Lake Missoula was therefore not a single threat, but a recurring one. It represented a system caught between slow and fast processes. Ice accumulated and flowed slowly. Water collected slowly. But when release came, it was abrupt and decisive. This pattern highlights a broader truth about the end of the Ice Age. Change did not proceed smoothly from frozen to unfrozen. It advanced through pauses and pulses. Periods of relative calm were punctuated by dramatic events that redistributed energy and matter far more efficiently than gradual melting alone could have achieved. Lake Missoula also demonstrates how geography matters. Not every ice-dammed lake became a source of megafloods. The size of the basin, the height of the dam, the available drainage routes, and the regional climate all influenced outcomes. In this case, everything aligned to create a system capable of extraordinary releases. The lake's existence depended on the persistence of the Cordilleran ice sheet. As long as that ice remained thick enough to block drainage, Lake Missoula would return, but each flood chipped away at that persistence. Ice lost mass, flow patterns shifted. Eventually, the ice dam could no longer reform at its previous strength. Even before the final disappearance of the dam, the system began to change. Floods became less frequent or smaller. The lake may have filled to lower levels. Drainage pathways became more permanent. The water that once waited so long behind ice found ways to escape more gradually. Still, during its most active phase, Lake Missoula stands as a reminder that some of the most powerful forces in Earth's history arise not from constant motion, but from restraint. Water confined, pressured, and delayed can do more work in a few days than unconfined water can do in centuries. When the water finally escaped its confines, it did not behave like a river swollen by rain or a lake spilling gently over its banks. It behaved like something released from obligation. What had been held back for years, sometimes centuries, moved all at once, guided only by gravity and shaped by the land in its path. These were not singular events, but a sequence of releases that unfolded whenever conditions aligned just enough for restraint to fail again. Together they are remembered as the Great Floods, not because they happened everywhere at once, but because of what they did, how fast they did it, and how completely they changed the places they touched. Once the ice dam failed, water accelerated immediately. The initial breach may have begun beneath the ice, hidden from view, but the effect on the lake was swift. As soon as the stable drainage pathway opened, lake levels began to drop. Falling water increased the pressure gradient driving flow, which in turn increased erosion within the channel. Ice melted faster. Sediment was torn free. What started as confined flow became an expanding conduit, and then an open surge. The volume of water involved defies easy comparison. Lake Missoula alone held more water than many of the largest modern freshwater lakes combined. When released, that water did not trickle downstream over weeks or months. It surged out in a matter of days, possibly hours at peak discharge. Estimates suggest that peak flow rates rivaled or exceeded the combined discharge of all modern rivers on Earth. Even allowing for uncertainty, the scale is difficult to exaggerate. As the flood waters burst from the lake basin, they followed the natural topography, but with an intensity that overwhelmed it. Valleys that once guided modest rivers suddenly became conduits for walls of water hundreds of meters deep. The flow did not neatly fill channels. It spilled outward, overtopping ridges, exploiting low points, and carving entirely new routes. In places, water rose high enough to submerge hills, turning complex terrain into temporary inland seas. The speed of the flood varied depending on slope and confinement. In narrow valleys, water accelerated dramatically, scouring bedrock and carrying enormous loads of debris. In wider basins, the flow spread and slowed somewhat, depositing sediment in thick layers before surging onward again. This alternation between erosion and deposition left behind a patchwork of features that would later puzzle geologists, accustomed to thinking in terms of slow processes. One of the most striking characteristics of these floods was their ability to move material that would normally be immobile. Boulders weighing hundreds of tons were lifted and transported. Some were rolled along the bottom, grinding against bedrock. Others were suspended briefly in turbulent flow before being dropped far from their source. These erratics, scattered across landscapes, where no local rock matched them, became silent witnesses to forces far beyond ordinary floods. The water was not clear. It carried immense quantities of sediment, from fine glacial flour to coarse gravel and rock fragments. This sediment made the floodwaters abrasive. As they moved, they sand-blasted rock surfaces, polishing them smooth and carving long parallel grooves aligned with flow direction. These grooves, still visible today, in some regions, record not just the presence of water, but its speed and persistence. In many places, the floods carved channels that seem absurdly oversized compared to the streams that occupy them now. These channels can be kilometers wide and tens of meters deep. Yet today, they may hold only small rivers or remain dry entirely. Their scale only makes sense when viewed through the lens of catastrophic flow. No amount of gradual river erosion could explain them within the available time. As floodwaters raced westward from the Lake Missoula Basin, they entered what is now eastern Washington. Here the landscape offered a particularly dramatic canvas. Basalt plateaus laid down by ancient volcanic eruptions were relatively flat but fractured. The floods exploited these fractures, stripping soil, plucking blocks of rock, and carving a maze of channels that diverged and rejoined repeatedly. This region, now known as the Schnee-Led Scablands, bears some of the clearest evidence of mega-flood activity on Earth. In the Scablands, water did not simply carve a single dominant channel. It spread across the plateau, finding multiple paths. Some channels captured more flow and deepened rapidly. Others carried less water, but still enough to strip vegetation and soil. The result was a complex network of coulees, dry falls, and streamlined hills, all shaped in the direction of flow. Dry falls provide a particularly vivid example. These are enormous cliff-like features that resemble waterfalls frozen in time. Some are far larger than any modern waterfall, with widths of several kilometers and drop heights exceeding 100 soaring. They formed where floodwaters plunged over resistant rock layers, eroding softer material downstream and causing the falls to retreat upstream rapidly. This retreat could happen astonishingly fast under such conditions, carving vast amphitheater-shaped cliffs in days. Downstream of these falls, plunge pools formed, scoured deep by turbulent water. The size of these pools reflects the energy involved. Some are large enough to swallow modern stadiums. Today, they may be dry or filled with sediment, but their shapes remain unmistakable. As the floods continued, they encountered areas where the land dipped below the flood level, creating temporary lakes. Water pulled in these basins, slowing and depositing sediment. Fine-grained layers settled out, while coarser material was dropped closer to flow margins. When water levels rose high enough, these temporary lakes spilled over their own low points, releasing secondary floods that added complexity to the overall pattern. Eventually, floodwaters reached the Columbia River Valley and beyond, pouring into the Pacific Ocean. The arrival of such vast quantities of fresh water into the ocean would have had immediate and far-reaching effects. Ocean salinity dropped locally. Stratification increased. Currents driven by density differences were disrupted. These changes likely rippled outward, influencing climate patterns on timescales ranging from years to centuries. But the floods did not happen just once. This is a crucial point. After each release, the ice dam reformed, the lake refilled, and the cycle repeated. Each flood followed broadly similar routes, but not identical ones. Small differences in topography, sediment distribution, and remaining ice altered flow paths slightly each time. Over repeated events, these variations compounded, widening channels, deepening basins, and smoothing obstacles. The repetition of floods also explains why the landscape looked so thoroughly reworked. A single flood, no matter how large, would leave dramatic features, but repeated floods reinforce them. They remove material loosened by earlier events. They extend channels farther upstream and downstream. They erase evidence of intermediate stages, leaving behind landforms that appear to have been shaped in one continuous act. For those living nearby at the time, these floods would have been terrifying beyond description. Even if people were not present in the direct path, the effects would have been visible from afar. The sound of rushing water would carry for vast distances. Dust and mist would rise into the air. Rivers far downstream would swell suddenly. Familiar landmarks would vanish. And yet, between floods, the world would return to a kind of uneasy normal. The lake would refill slowly. Vegetation might begin to recolonize disturbed areas. Animals would return to altered but still usable landscapes. This alternation between catastrophe and calm would leave deep impressions on memory and culture, reinforcing the sense that water was both life-giving and dangerously powerful. From a geological perspective, the great floods accomplished in short bursts what would otherwise require immense spans of time. They redistributed sediment across regions. They carved drainage networks that still influence river paths today. They lowered divides, allowing waterheads to reorganize permanently. In doing so, they accelerated the reshaping of continents in a way that aligned with the broader climatic transition underway. The floods also played a role in the retreat of ice itself by removing large volumes of water from behind ice dams. They reduced pressure locally, altering ice flow upstream. Each flood event removed ice mass indirectly by transferring meltwater to the oceans, contributing to sea level rise. Over time, these pulses added up, helping to destabilize ice sheets more broadly. It is important to recognize that these floods were not anomalies in an otherwise gentle deglaciation. They were part of the system's natural response to changing conditions. When ice could no longer release water slowly enough, it released it quickly. The physics of flow took over, indifferent to scale or consequence. As scientists pieced together this story, it challenged long-held assumptions about how landscapes change. For a long time, geology favored gradualism. The idea that slow processes operating over long periods explained most features. The evidence of the great floods forced reconsideration. It showed that rare high-magnitude events can dominate landscape evolution, even if they occur over relatively short intervals. This does not mean that gradual processes are unimportant. On the contrary, the floods were made possible by long-term accumulation of ice and water. Without tens of thousands of years of cold, there would have been no lake to drain. Without slow tectonic shaping of the basin, there would have been nowhere for water to collect. The floods were fast, but they were built on slow foundations. As the sequence of floods continued, their character likely evolved. Early floods may have been larger when lakes reached their maximum levels. Later floods may have been smaller or more frequent as drainage pathways became more established and ice dams weakened. Eventually, the ice could no longer reform effectively and the cycle ended. By that point, the damage, or perhaps more noodly, the work had been done. Landscapes were transformed. Water pathways were rewritten. The region bore the unmistakable signature of flow that was anything but ordinary. Looking beyond this specific case, similar processes occurred elsewhere as the Ice Age waned. Other glacial lakes formed and drained catastrophically in different parts of the world, though few matched the scale of Lake Missoula's floods. Together, these events formed a pattern. As ice sheets destabilized, water became a primary agent of change. What remains striking is how much of this story is still visible. You can stand today in regions shaped by these floods and see the evidence directly. Channels too large for their rivers, hills sculpted into streamlined forms, boulders perched improbably on plateaus. These are not subtle clues. They're bold signatures of a world in transition. The great floods were therefore not just local disasters or geological curiosities. They were integral steps in the planet's movement out of the Ice Age. They represent moments when stored change was released all at once, pushing the system forward faster than gradual processes alone ever could. When the floodwaters withdrew, they did not leave behind a gentle hint of their passing. They left a landscape that no longer made sense under the old rules. Valleys were far too wide for the rivers that occupied them. Hills were shaped as if pressed by an invisible hand. Rock surfaces were smoothed, grooved, and stripped of soil as though time itself had accelerated and then stopped abruptly. What had taken shape over days now looked as if it should have required ages. This was the aftermath of water, moving faster and with more force than the land had ever experienced before. To appreciate how unusual these landscapes are, it helps to think about how landforms normally develop. Under ordinary conditions, rivers carve valleys gradually. They meander, erode banks slowly, deposit sediment downstream, and respond to changes in climate over long spans of time. Even powerful seasonal floods usually add only incremental change. Hills are worn down grain by grain. Channels migrate centimeter by centimeter. Landscapes tell stories written patiently. The terrain left behind by the great floods told a different kind of story. Here, erosion was not incremental. It was wholesale. Soil layers that had taken thousands of years to form were removed almost instantly. Vegetation was not trimmed or damaged. It was erased. In many places, the floods cut directly into bedrock, bypassing softer material entirely. The result was a stripped landscape where the geological skeleton lay exposed. One of the most striking features created by these events is the sheer scale mismatch between landforms and modern processes. Channels carved by the floods can be kilometers wide and dozens of meters deep. Yet today, they may carry only small streams or remain dry year-round. These oversized channels are not anomalies. They are consistent across regions affected by megafloods, forming networks that only make sense when viewed as products of catastrophic flow. The water that carved these channels did not behave like a typical river. It was turbulent, chaotic, and laden with debris. As it moved, it scoured the land unevenly, deepening some paths, while leaving adjacent areas relatively untouched. This created a braided pattern of erosion, with multiple channels diverging and rejoining, sometimes abruptly. Unlike meandering rivers, which curve gently, flood channels often cut straight paths, ignoring subtle variations in slope. Where the floodwaters encountered resistant rock layers, they did not simply slow down. They attacked weaknesses. Fractures, joints, and faults in the bedrock became points of leverage. Water forced its way into cracks, prying loose blocks of stone. Once loosened, these blocks were carried away or rolled along the bottom, further eroding the surface. This process, known as plucking, allowed floods to dismantle bedrock in a way ordinary rivers rarely can. In places where the floods spilled over cliffs or steep drops, waterfalls formed on a scale rarely seen today. These were not stable features. The immense energy of falling water eroded the base of the falls, rapidly undercutting the rock above. As support was removed, the cliff face collapsed and the waterfall retreated upstream. This retreat could happen astonishingly fast, meters per day, under peak conditions, carving enormous amphitheaters in a matter of days. Once the floodwaters moved past these drops, they often formed deep plunge pools. These basins were scoured by swirling high-energy flow, sometimes reaching depths of tens of meters. The size of these pools reflects the violence of the process. In many cases, the plunge pools are far larger than those formed by any modern waterfall, underscoring the difference in scale between ordinary flow and mega floods. Not all areas experienced deep erosion. In some regions, the floods deposited vast quantities of sediment instead. When water slowed, either because it spread out over flatter terrain or entered temporary lakes, it dropped its load. Coarse material settled first, forming gravel bars and boulder fields. Finer sediment settled later, forming layered deposits that record individual flood events. These layers, stacked one atop another, provide a timeline of repeated flooding. The shapes of hills left behind by the floods are another distinctive signature. In areas where water flowed rapidly over loose sediment, it sculpted streamlined forms known as flood bars, or longitudinal ridges. These hills are elongated in the direction of flow, with blunt upstream ends and tapered downstream tails. Their shapes reflect the movement of water around them, much like ripples in sand, but on a scale measured in hundreds of meters. Even bedrock hills were reshaped. Where rock resisted complete removal, it was smoothed and streamlined. Sharp edges were rounded. Surfaces were polished. Long grooves, aligned with the direction of flow, were etched into the stone by sediment carried at high speed. These grooves are often remarkably straight and parallel, indicating sustained directional flow rather than chaotic movement. Another feature commonly left behind is the presence of erratic boulders. These are large rocks deposited far from their source, often perched in places that seem improbable. Some sit at top hills or plateaus far above any modern river. Their presence makes sense only when considering water levels hundreds of meters higher than today, capable of lifting and transporting such massive objects. The floods also reorganized entire drainage systems. Rivers that once followed one path found themselves diverted into newly carved channels. Waterhead shifted. In some cases, drainage divides were lowered or removed entirely, allowing water to flow in directions it never had before. These changes persisted long after the floods ended, shaping how water moved through the landscape up to the present day. What makes these landscapes particularly compelling is how abruptly they were formed. Evidence suggests that individual flood events could carve major features in days or weeks. Repeated floods amplified these effects, but even a single event could leave a lasting mark. This rapid transformation stands in stark contrast to the slow pace we usually associate with geological change. For a long time, this posed a problem for scientists. Early geologists trained to think in terms of gradual processes struggled to explain these features. Oversized channels, immense plunge pools, and streamlined hills seemed incompatible with known river behavior. Some proposed exotic explanations. Others dismissed the features as anomalies. It took careful mapping, sediment analysis, and an openness to rare but powerful events to assemble the true story. Once understood, the implications were profound. These landscapes demonstrated that rare, high-energy events can dominate geological change, even if they occur infrequently. A few days of extreme flooding can accomplish more erosion and deposition than thousands of years of normal river flow. This does not negate the importance of gradual processes, but it reframes them as part of a spectrum rather than the whole story. For ecosystems, the immediate aftermath of the floods would have been stark. Large areas were stripped bare, reduced to rock and gravel. Soil development had to begin again from scratch. Plants recolonized slowly, starting with hardy pioneer species capable of surviving in poor substrates. Animals returned as vegetation recovered, following new routes shaped by altered terrain. Over time, life adapted to the new landscapes. Rivers settled into oversized channels, occupying only a fraction of the space carved for them. Wetlands formed in depressions left by erosion. Lakes filled plunge pools and scoured basins. The scars of flooding softened, but they did not disappear. For humans living in or near these regions, the transformed landscape would have influenced movement, settlement, and resource use. New river courses changed access to water. Altered terrain affected travel routes. Areas stripped of soil would have been less productive for generations. Memories of the floods passed down orally may have blended with the visible evidence left behind, reinforcing cultural narratives about powerful waters. It is important to recognize that these landscapes were not mistakes or accidents. They were logical outcomes of the forces at play. Water given enough volume and speed will reshape land efficiently. The unusual aspect here was not the behavior of water, but the conditions that allowed such vast quantities to move so quickly. As the Ice Age continued to wane, the role of these carved landscapes did not end. They influenced subsequent events. Channels created by early floods guided later ones, focusing flow and increasing efficiency. Valleys deepened by water became pathways for rising seas as global levels increased. The work done in days had consequences lasting thousands of years. These landscapes also provide a form of memory for the planet. Long after the ice melted and the flood ceased, the land retained the imprint of those moments. Geologists can read this imprint like a record, reconstructing events that happened too fast for direct observation. In this way, stone becomes an archive of speed. For a long time, the oceans barely seemed to notice what was happening on land. Ice sheets waxed and waned. Lakes formed and drained. Floods tore across continents. Yet, when measured year to year, the global sea level appeared stubbornly steady, held low by the sheer amount of water still trapped as ice. This apparent calm can be misleading because the oceans respond not to moments but to accumulation. And once accumulation reaches a certain point, change accelerates. At the height of the Ice Age, sea levels sat far below where they are today. Vast quantities of water were locked up in continental ice sheets, especially in the northern hemisphere. The oceans, deprived of this water, retreated from their modern coastlines, exposing continental shelves and reshaping global geography. For thousands of years, this condition persisted. Even as ice began to thin in places, the oceans remained low because the system was still dominated by storage rather than release. The earlier stages of ice loss did not translate immediately into rising seas. Much of the meltwater produced during initial warming never reached the ocean at all. It pulled in inland basins, soaked into sediments, or became trapped behind ice dams like the one that formed Lake Missoula. In other regions, meltwater flowed into enclosed seas or cold polar oceans, where extensive sea ice limited mixing. The oceans were receiving water, but not in a way that dramatically changed their overall volume. This is why the first phase of sea level rise after the Ice Age began was slow. It unfolded over centuries, almost imperceptible within a human lifetime. Coastlines shifted inward by small amounts. Estuaries deepened slightly. Tidal patterns adjusted for coastal ecosystems and human populations living far inland due to the lowered seas. These changes were background noise rather than crisis. But beneath this slow response, a threshold was forming. As warming continued, ice loss accelerated. Ice sheets thinned not just at their edges, but across broader regions. Glaciers retreated into higher elevations, where accumulation zones shrank. The balance tipped increasingly toward net loss. Meltwater production increased, and more of that water found direct pathways to the ocean. The Great Floods played a crucial role in this transition. Each megaflood delivered an enormous pulse of fresh water to the sea in a matter of days. Individually, these pulses may not have raised global sea level by dramatic amounts, but collectively, they mattered. They transformed a slow trickle into a stepwise rise. Sea level did not climb smoothly. It jumped, paused, and jumped again. When large volumes of fresh water entered the oceans rapidly, the effects went beyond simple addition of water. Fresh water is less dense than salt water, so it tends to remain near the surface. This stratification reduced vertical mixing, particularly in regions critical for deep water formation. Ocean currents that rely on dense, salty water, sinking to drive circulation, slowed or shifted. These circulation changes fed back into the climate system. Reduced heat transport toward high latitudes could temporarily cool certain regions, even as the planet warmed overall. Such cooling episodes may explain why the end of the Ice Age was not a smooth warming trend, but a sequence of advances and retreats. Warm periods interrupted by sudden cold snaps. Despite these complexities, the long-term direction was clear. More ice was melting than reforming. More water was entering the oceans than leaving them. Sea level began to rise more consistently. As it did, the rate of rise increased. One reason for this acceleration lies in geometry. As ice sheets shrink, they expose darker land and water surfaces that absorb more sunlight. This additional absorption enhances warming, which accelerates melting further. The process feeds on itself. Meanwhile, as sea levels rise, ocean water comes into contact with ice margins in coastal regions, increasing melting from below and from the sides. Ice that once ended on land now ends in water, where it is more vulnerable. Another factor is the loss of buttressing. Large ice shells, floating extensions of ice sheets, can slow the flow of ice from land into the sea by providing resistance. As these shelves thin or collapse due to warming water, the ice behind them flows faster. This increases the rate at which land-based ice enters the ocean, further accelerating sea level rise. The oceans themselves contribute to this acceleration through thermal expansion. As water warms, it expands. Even without adding new water from melting ice, warming alone causes sea level to rise. During the transition out of the Ice Age, ocean temperatures increased gradually, adding another component to the overall rise. Taken together, these processes transformed sea level rise from a slow adjustment into a more rapid one. Over the course of several thousand years, sea levels rose by more than 100 meters. But this rise was not evenly distributed across time. There were periods when levels climbed relatively quickly, separated by intervals of slower change. For coastal landscapes, this meant repeated reorganization. Shorelines migrated inland. River mouths shifted. Low-lying areas flooded, sometimes temporarily, sometimes permanently. Coastal ecosystems had to move or adapt. Coral reefs, which grow upward towards sunlight, raced to keep pace with rising water, succeeding in some regions and drowning in others. For human populations, rising seas were transformative. Areas that had been inhabited for generations were gradually inundated. Land bridges disappeared, isolating populations that had once been connected. Coastal routes changed, resources shifted. People adapted by moving, altering subsistence strategies, and reshaping cultural practices. What makes this transition particularly striking is the contrast between its beginnings and its later stages. At first, the oceans rose almost politely, as if testing boundaries. Later, they advanced with confidence, reclaiming land that had been exposed for tens of thousands of years. This contrast reflects the non-linear nature of Earth systems. Change can be slow until it isn't. It is also important to recognize that sea level rise was not uniform across the globe. The presence and disappearance of ice sheets affected local sea levels through gravitational effects. Large ice masses exert a gravitational pull on nearby ocean water, causing sea levels to be higher near the ice and lower farther away. As ice melted, this pull weakened, causing sea levels to fall locally, even as they rose globally. In addition, the rebound of land previously depressed by ice altered relative sea levels. As the crust slowly rose after ice loss, some coastal regions experienced less flooding than expected, or even temporary emergence of land. Elsewhere, subsiding land amplified the effects of rising seas. The result was a patchwork of experiences, with some regions flooding rapidly, while others changed more gradually. Despite this variability, the overall trend reshaped the planet. Continental shelves that had been exposed during the Ice Age were submerged once again. River valleys carved during low sea levels became estuaries. Sediment deposited by floods and rivers was reworked by waves and tides, forming new coastlines. The oceans, once reduced and distant, expanded back toward their modern extent. Their return was not an invasion, but a restoration of a long-standing balance, albeit under warmer conditions than before. The water that had been locked away returned to circulation, reconnecting Earth's hydrological system. Yet this reconnection carried consequences. Rising seas altered salinity patterns, nutrient distributions, and marine habitats. Coastal upwelling zones shifted. Fisheries changed. The timing and location of biological productivity adjusted to new conditions. From a planetary perspective, the acceleration of sea level rise marked a tipping point. It signaled that ice was no longer the dominant reservoir of fresh water. The oceans had resumed their role as the primary holder of Earth's liquid water. This shift stabilized some aspects of the climate, while destabilizing others, contributing to the complex pattern of change that characterized the end of the Ice Age. What stands out most is how gradual processes and abrupt events intertwined. Slow warming set the stage. Ice thinned incrementally, then floods delivered water in pulses. Sea levels responded with steps, rather than a smooth curve. Acceleration emerged from accumulation. As the oceans continued to rise, they began to influence the climate in new ways. Increased ocean surface area enhanced evaporation, feeding more moisture into the atmosphere. This moisture supported precipitation patterns that differed from those of the Ice Age, further reshaping ecosystems and ice behavior. The system was moving toward a new equilibrium, but it had not reached it yet. The rising oceans also carried memory. Chemical signatures in marine sediments recorded pulses of fresh water. Microfossils preserved shifts in temperature and salinity. These records allow scientists to trace not just how much the sea rose, but how quickly and under what conditions. As the oceans absorbed the returning water, the effects did not remain confined to coastlines or local currents. Water added to the ocean in large sudden pulses behaves differently from water added gradually, and the climate system is sensitive to that difference. What followed the Great Floods was not a simple warming trend, marching steadily forward, but a series of reactions that rippled outward across the planet. These reactions can be thought of as climate shock waves, not explosive events, but far-reaching adjustments that traveled through air, sea, and ice, altering conditions in places far removed from the original source. One of the most immediate consequences of massive freshwater input into the oceans was a change in how those oceans circulated. Ocean circulation depends heavily on differences in temperature and salinity. Warm water tends to stay near the surface. Cold, salty water is denser and sinks, driving deep currents that move heat around the globe. This system, often described as a conveyor, plays a central role in regulating Earth's climate. When enormous volumes of fresh water entered the oceans, particularly in the North Atlantic and connected basins, that balance was disrupted. Fresh water is less salty and therefore less dense. When it spread across the ocean surface, it formed a lighter layer that resisted sinking. This inhibited the formation of deep water in regions where it normally occurred. As a result, the conveyor slowed or shifted. A slowdown in ocean circulation does not simply cool or warm the planet evenly. It redistributes heat. Regions that once received a steady supply of warm water from lower latitudes could cool significantly, even as the planet as a whole continued to warm. Other regions might warm faster as heat accumulated. These uneven changes are why the end of the Ice Age was marked by sudden climate reversals rather than a smooth transition. One of the clearest examples of such a reversal is a period known as the Younger Dryas. After thousands of years of gradual warming, parts of the northern hemisphere experienced a rapid return to cold conditions. Temperatures dropped sharply in regions surrounding the North Atlantic. Glaciers stabilized or advanced briefly, and ecosystems adjusted once again to colder, drier conditions. This cooling lasted for over 1,000 years before warming resumed. While the exact causes of the Younger DUS are still debated, massive freshwater input from glacial lakes and melting ice is widely considered a key factor. By disrupting ocean circulation, these freshwater pulses reduced heat transport to high latitudes, triggering regional cooling. The fact that such a dramatic shift could occur relatively quickly highlights the sensitivity of the climate system to changes in ocean conditions. These shock waves were not limited to the northern hemisphere. Changes in ocean circulation affected atmospheric circulation as well. The atmosphere responds quickly to changes in temperature gradients. When ocean heat distribution shifted, wind patterns adjusted, storm tracks moved, monsoon systems weakened or strengthened, depending on how land and sea temperatures changed relative to one another. In the tropics, altered circulation influenced rainfall patterns. Some regions experienced increased precipitation, while others became drier. Lake levels rose and fell in response. Vegetation zones shifted. These changes are recorded in pollen deposits, lake sediments, and cave formations, which show alternating wet and dry phases during the transition out of the Ice Age. In the southern hemisphere, the effects were felt differently, but no less profoundly. Changes in northern ocean circulation can influence southern systems through a process sometimes called the bipolar seesaw. When the North Atlantic cools due to reduced heat transport, the southern hemisphere can experience warming and vice versa. This redistribution of heat reflects the interconnected nature of Earth's climate. Ice cores from Antarctica show warming trends that do not always align perfectly with those in Greenland. These differences are not contradictions. They are signatures of heat being moved around rather than created or destroyed. The floods and meltwater pulses helped tip these balances, shifting where heat accumulated. Sea ice also played a role in amplifying climate shock waves. As freshwater input increased and ocean circulation slowed, sea ice expanded in some regions. Sea ice reflects sunlight and insulates the ocean below, reinforcing cooling. Expanded sea ice also affects atmospheric circulation by altering temperature gradients and surface roughness. These feedbacks could lock regions into colder states for extended periods. At the same time, in areas where sea ice retreated due to overall warming, the opposite feedback occurred. Dark ocean water absorbed more sunlight, accelerating warming locally. The coexistence of expanding ice in some regions and retreating ice in others illustrates how uneven and complex the transition was. On land, ecosystems responded to these shifting conditions with remarkable sensitivity. Plants migrate slowly compared to animals, but they respond strongly to changes in temperature and moisture. Pollen records show that forests advanced, retreated, and advanced again in response to climate oscillations. Grasslands expanded during drier periods and shrank during wetter ones. These changes cascaded through food webs, affecting herbivores and the predators that depended on them. Large mammals already adapted to cold conditions face shifting habitats. Some species thrived briefly during cooler reversals, while others struggled as warming resumed. Extinctions that occurred near the end of the Ice Age likely reflect a combination of climate stress and human pressure, with rapid environmental change reducing resilience. For human populations, these climate shock waves shaped movement, innovation, and survival strategies. Groups living at the margins of ice sheets or insensitive ecosystems had to respond to changing resources. Shifts in rainfall altered the availability of plants and animals. Changing coastlines affected access to marine resources. Rivers changed course, influencing travel and trade routes. The unpredictability of climate during this period may have favored flexibility. Populations that could adjust their subsistence strategies, move when necessary, and share knowledge across groups, were better positioned to cope. Cultural memory preserved through stories and traditions may have encoded lessons about floods, cold snaps, and the dangers of environmental instability. It is important to note that these shock waves were not uniformly destructive. In some regions, changing conditions created new opportunities. Retreating ice exposed fertile land. Increased rainfall supported new plant growth. Rising seas created productive coastal environments. The same processes that disrupted established systems also laid the groundwork for new ones. From a global perspective, the climate system during this time behaved less like a thermostat and more like a complex network responding to multiple inputs. Freshwater pulses from melting ice acted as sudden disturbances. The system absorbed these disturbances, redistributed energy, and settled into new configurations only to be disturbed again. These repeated adjustments explain why the end of the Ice Age unfolded over thousands of years rather than resolving quickly once warming began. Each major pulse of change altered conditions enough to affect the next phase. The system did not simply slide downhill toward warmth. It stepped, paused, and sometimes slipped backward before moving forward again. The concept of climate shock waves helps clarify why distant regions can experience dramatic change in response to events that occur far away. Water released from glacial lakes in North America influenced rainfall in Africa. Ice retreat in the Northern Hemisphere affected temperatures in the South. The planet systems are tightly coupled, even when connections are not immediately obvious. Evidence for these connections comes from multiple sources. Ice cores record changes in atmospheric composition and temperature. Marine sediments preserve shifts in ocean chemistry and circulation. Terrestrial records such as pollen and lake levels document changes in vegetation and hydrology. When these records are aligned, patterns emerge that point to rapid global responses to freshwater input and ice loss. One of the lessons from this period is that stability can be deceptive. For long stretches, conditions may appear steady, only to change rapidly when thresholds are crossed. The climate system can store imbalance, much like ice stores water, releasing it abruptly when conditions allow. As the Ice Age drew closer to its end, these shock waves gradually diminished in intensity. Ice sheets shrank enough that massive sudden freshwater pulses became less common. Ocean circulation stabilized into patterns more familiar today. Temperature fluctuations became smaller. The system began to settle. But the memory of those shock waves remains written into the geological record. They remind us that climate change is not always slow or smooth. It can involve sudden reorganizations driven by processes that operate out of sight until their effects are felt everywhere. When the ice loosened its hold, life did not rush back all at once, and it did not do so triumphantly. What followed was not a sudden greening of the world, but a careful, uneven process of adjustment. The planet that emerged from beneath the ice was not the same planet that had gone into it. Landscapes were reshaped, climates were unsettled, and familiar patterns no longer applied. Life after the ice was not a return to normal. It was an experiment carried out across continents, one species, one ecosystem, one generation at a time. As glaciers retreated, they revealed ground that had not seen sunlight for tens of thousands of years. In some places, this ground was raw bedrock, scraped clean by ice and water. In others, it was a chaotic mix of gravel, sand, and fine sediment deposited by meltwater. These surfaces were unstable, prone to erosion, and largely devoid of nutrients. For plants, this presented a challenge that could not be solved quickly. The first colonizers were not trees or lush grasses, but organisms adapted to hardship. Mosses, lichens, and hardy pioneer plants took hold where they could, anchoring themselves in cracks and thin soils. Their role was not dramatic, but it was essential. By growing, dying, and decomposing, they began the slow process of soil formation. Organic matter accumulated. Microbial communities developed. Over time, these processes transformed barren surfaces into environments capable of supporting more complex life. As conditions improved, grasses and shrubs followed. These plants spread gradually, responding to temperature, moisture, and the availability of sunlight. Their expansion was not uniform. In some regions, warming temperatures favored rapid growth. In others, dry conditions limited progress. Vegetation zones shifted northward and upward in elevation, tracking climate changes with a lag that sometimes spanned centuries. Trees arrived later. Still, forests did not surge forward as a single front. They advanced in fits and starts, influenced by local conditions and barriers created by newly formed rivers, lakes, and wetlands. Pollen records show that forests retreated during cold reversals and advanced again during warmer periods. The composition of these forests changed over time, reflecting both climate and chance. Species that arrived first often dominated until conditions shifted enough to favor others. Animals followed the vegetation, but not always predictably. Large herbivores depended on grasses and shrubs that spread across deglaciated plains. As these food sources expanded, so did the animals that relied on them. In some regions, herds grew large, moving across open landscapes shaped by floods and glacial retreat. Predators followed, adapting their hunting strategies to new terrain. Yet, not all species thrived. The end of the Ice Age coincided with the decline and extinction of many large mammals. Mammoths, mastodons, giant ground sloths, and other megafauna disappeared from much of their former range. The causes of these extinctions are complex and likely varied by region. Climate change altered habitats rapidly, reducing suitable environments. Human hunting added pressure. The combination proved too much for some species, especially those with slow reproductive rates. Smaller animals often fared better. Their ability to reproduce quickly, exploit diverse food sources, and occupy a range of habitats gave them flexibility. Birds expanded into new nesting areas as ice retreated. Fish recolonized rivers and lakes formed by glacial melt. Insects spread alongside plants, playing crucial roles in pollination and nutrient cycling. Aquatic ecosystems experienced their own transitions. Newly formed lakes, carved by ice, or scoured by floods filled with meltwater. At first, these lakes were cold, turbid, and low in nutrients. Over time, sediments settled, water clarity improved, and biological productivity increased. Algae established themselves, followed by invertebrates and fish. Each lake followed its own trajectory, influenced by depth, drainage, and connection to other water bodies. Rivers also changed character. Channels carved by floods were often oversized, holding far less water than their dimensions suggested. These rivers adjusted slowly, depositing sediment, forming new banks, and developing meanders within the larger flood-carved valleys. Floodplains formed, providing fertile ground for plants and animals alike. Wetlands became increasingly common as rising water tables and uneven terrain created shallow basins. These wetlands supported rich biodiversity. They acted as filters for water, trapping sediment and nutrients. They also provided stable resources for animals and eventually humans. For human populations, life after the ice required flexibility and awareness. The environments they encountered were dynamic and sometimes unpredictable. Resources shifted with changing climates. Coastlines moved. Rivers changed course. Familiar hunting grounds disappeared while new ones emerged. Humans responded by adapting their strategies. In some regions, people followed large game across open landscapes, adjusting routes as vegetation changed. In others, they diversified their diets, incorporating plants, small animals, and aquatic resources. Tool technologies evolved in response to new materials and needs. Clothing, shelters, and food storage methods reflected local conditions. As seas rose, coastal environments became increasingly important. Estuaries, tidal flats, and shallow seas supported abundant life. Fish, shellfish, and marine mammals provided reliable food sources. Human groups living near these environments developed new techniques for harvesting and processing marine resources. Coastal routes facilitated movement and exchange even as land bridges disappeared. Cultural traditions evolved alongside these changes. Knowledge of seasonal patterns, animal behavior, and plant growth became critical for survival. Oral traditions likely preserved information about past floods, cold snaps, and shifting landscapes. These stories served not just as explanations, but as guides for navigating a changing world. It is important to recognize that life after the ice was not universally easier. While some regions became more hospitable, others became more challenging. Increased rainfall in some areas led to flooding and erosion. Drier conditions elsewhere reduced water availability. The disappearance of large ice sheets altered wind patterns, affecting temperature and precipitation in ways that were not always favorable. The pace of change also mattered. Gradual shifts allowed ecosystems and human societies to adjust. Rapid changes, such as those associated with climate shock waves, forced abrupt responses. Species and populations unable to adapt quickly faced decline or displacement. Despite these challenges, the overall trend favored diversification and expansion. As the climate stabilized into an interglacial state, new ecosystems emerged. Forests spread across regions once dominated by ice or tundra. Grasslands expanded in others. Biodiversity increased as niches multiplied. This period also laid the groundwork for later developments. Stable climates and productive ecosystems supported growing human populations. Over time, some groups began to settle more permanently, experimenting with cultivation and animal management. These developments did not happen immediately, nor everywhere, but the conditions that made them possible emerged from the post-ice landscape. What stands out about life after the ice is its resilience. The transition out of the Ice Age involved disruption, loss, and uncertainty. But life persisted. It adapted, reorganized, and found new ways to thrive. The planet did not simply recover from the Ice Age. It transformed. This transformation was not guided by a single direction or outcome. It was shaped by local conditions, chance events, and interactions among species. Some paths led to flourishing ecosystems. Others ended in extinction. Together, they formed a mosaic of responses that defined the early Holocene world. Long after the ice retreated and the waters settled into their new paths, something remained that did not erode, melt, or drain away. Memory stayed. Not memory in the sense of written records or measured timelines, but memory carried by people, shaped by experience, and passed from one generation to the next through stories. As landscapes changed and climate stabilized, humans continue to tell accounts of overwhelming water, lost lands, and moments when the world seemed to break and then begin again. These stories appear across cultures separated by vast distances. And while they differ in detail, they share a strikingly similar core. It is tempting to dismiss flood stories as coincidence or imagination. But doing so overlooks how humans remember environmental change. Long before writing, people preserved knowledge through narrative. Stories were not entertainment alone. They were tools for survival, ways of encoding information about danger, geography, and history in a form that could be remembered and retold accurately enough to matter. When an event was large enough, frightening enough, and disruptive enough, it earned a permanent place in that shared memory. The floods associated with the end of the Ice Age fit this category precisely. They were rare within a human lifetime, but not rare across generations. A single community might experience one catastrophic flood, recover, and then see another generations later. Over time, the memory of repeated events would compress into a single story of a great flood. Not because people misunderstood what happened, but because stories naturally simplify repeated experiences into archetypes. As sea levels rose and coastlines shifted, entire regions that had once been inhabited were slowly drowned. These were not sudden disasters, but gradual losses. Low-lying plains, once rich with resources, became wetlands, then shallow seas. Rivers widened into estuaries. Familiar landmarks vanished beneath water. People living through these changes would not have perceived them as abstract trends. They would have experienced them as loss. Loss of land, loss of roots, loss of places tied to identity. When those experiences were remembered, they were remembered emotionally rather than numerically. A place that disappeared over several generations might be recalled as a land taken by the sea. A river that surged beyond anything previously known might be remembered as a flood that covered the world. Memory does not preserve rates. It preserves impact. Across Mesopotamia, flood stories speak of a time when water rose high enough to destroy cities and wipe away civilization, sparing only those who were warned in advance. In South Asia, stories describe cycles of creation and destruction driven by water. In East Asia, ancient accounts tell of great floods that required heroic efforts to control and channel. In the Americas, indigenous traditions recount rising waters, lost lands, and ancestors who moved to higher ground. In Australia, oral histories describe coastline shifting and islands separating from the mainland, details that align remarkably well with known sea level rise. What is striking is not that these stories exist, but that many of them preserve geographical details consistent with post-Ice Age changes. Some coastal groups describe lands now underwater as former hunting grounds or campsites. Some stories place floods in specific valleys or river systems that we know were affected by meltwater surges. These are not vague myths floating free of place. They are anchored to real landscapes. This does not mean that every flood story is a literal account of a single event, like the draining of Lake Missoula. Human memory does not work that way. Instead, stories blend multiple experiences. A mega flood that carved a valley, a rising sea that swallowed a coastline, and a seasonal flood that destroyed a settlement might all merge into a single narrative of overwhelming water. The story becomes a container for many memories. The process by which this happens is subtle. Each retelling emphasizes what mattered most: fear, survival, loss, warning, renewal. Details that do not serve those themes fade. Details that reinforce them persist. Over time, the story stabilizes into a form that can endure centuries or even millennia. Importantly, these stories often include lessons. They warn about arrogance, about ignoring signs, about settling too close to water. They emphasize preparation, cooperation, and respect for forces beyond human control. These lessons are practical. They encourage behaviors that reduce risk in environments shaped by floods and changing water levels. In this way, flood stories function as cultural adaptations to a post-glacial world. They encode environmental knowledge in a form that is memorable, transmissible, and meaningful. They remind people that the world can change sometimes faster than expected, and that survival depends on paying attention. From a scientific perspective, the alignment between flood myths and post-Ice Age events has become increasingly difficult to ignore. Archaeology has uncovered submerged settlements along ancient coastlines. Geological evidence confirms rapid sea level rise and catastrophic flooding in multiple regions. Paleoclimate data shows abrupt shifts that would have been noticeable within human lifetimes. This does not require assuming that ancient people understood the physics of ice sheets or ocean circulation. They did not need to. They observed effects. They saw water rise where it had never risen before. They watched rivers behave unpredictably. They adapted and remembered. The idea that myth preserves truth does not mean that myths are factual reports. They are not. They are interpretations. But interpretations can still carry accurate information about what happened, especially when shaped by repeated experience. A story that warns of water returning again and again reflects a world where flooding was not a one-time anomaly, but a recurring reality. It is also worth noting that these stories often describe water as both destructive and renewing. Floods wipe away the old world, but they also create space for something new. Land emerges. Life continues. This duality mirrors what actually happened at the end of the Ice Age. Floods destroyed landscapes, but they also reshaped them into environments that supported future ecosystems and human societies. As writing emerged and societies became more complex, these stories were formalized, recorded, and sometimes moralized. Deities replaced natural forces. Floods became punishments or resets. Yet beneath the added layers, the core experience remains recognizable. Water rose, the world changed. Survivors remembered. In regions far from glacial lakes, sea level rise played a larger role in shaping flood memories. Coastal flooding occurred not as walls of water, but as relentless advance. A shoreline that moved a few meters per generation would still feel like loss. Over centuries, that loss would accumulate into stories of lands taken by the sea. For island communities, these changes were especially dramatic. As seas rose, islands shrank or vanished, travel routes changed, separation increased. Oral traditions describing former connections between islands and mainland have been corroborated by geological evidence showing submerged land bridges. These stories persisted because they explained why the world looked the way it did. Memory in this sense becomes a bridge between geology and culture. It connects physical events to human meaning. It allows experiences of the ice ages end to echo into historical times, even as the original landscapes disappeared. As we consider these stories, it becomes clear that the end of the Ice Age was not just a geological transition. It was a cultural one. Humans living through it developed new ways of understanding impermanence, risk, and resilience. Flood stories are artifacts of that learning process. They also remind us that the past is not as distant as it sometimes seems. The events that shaped these stories occurred within the span of human existence. They were witnessed, survived, and remembered by people not fundamentally different from us. The difference lies in scale and context, not in perception. When we listen to flood myths today, we're not hearing echoes of fantasy. We're hearing compressed histories of a planet in transition. The language is symbolic, but the experience is real. Water rose, ice vanished, land changed, people adapted. For a long time, it seemed as though the Ice Age might loosen its grip without ever fully releasing it. Ice sheets retreated, then paused. Temperatures rose, then dipped again. Floods surged, then quiet returned. The planet hovered in between states, no longer locked in deep cold, but not yet settled into warmth. And then gradually, but decisively, the balance shifted. The systems that had sustained the frozen world for tens of thousands of years lost their coherence. Ice, once the dominant organizer of climate, land, and water, began to step aside. This was not a single moment, but a drawn-out surrender. Uneven, irreversible, and quietly profound. The letting go of the Ice Age did not mean that ice vanished everywhere at once. Large ice sheets still covered substantial portions of the northern continents. Mountain glaciers persisted. Polar regions remained cold. What changed was not the presence of ice, but its authority. Ice no longer dictated global conditions. Instead, it reacted to them. One of the clearest signs of this transition was the breakdown of feedbacks that had once reinforced cold. During the height of the Ice Age, ice reflected large amounts of sunlight back into space. Snow-covered land and sea ice amplified this effect, keeping temperatures low. As ice retreated and thinned, darker surfaces were exposed. Soil, rock, vegetation, and open water absorbed more sunlight. This absorption increased surface temperatures, which accelerated melting further. The feedback loop that once favored ice now favored warmth. At the same time, greenhouse gas concentrations continued to rise. Carbon dioxide and methane levels increased as oceans warmed. Soils thawed and ecosystems expanded. These gases trapped more heat in the atmosphere, further weakening the conditions required for ice growth. Unlike earlier fluctuations, this warming was not offset by orbital configurations favoring cold. The long-term trend pointed clearly away from glaciation. Ice sheets responded unevenly. Their interiors, thick and elevated, remained cold longer. Margins thinned rapidly. Flow patterns changed as ice redistributed itself, retreating from lowlands and concentrating in higher regions. Ice streams, fast-flowing corridors within ice sheets, became more prominent, draining ice toward the sea efficiently. Where ice once moved slowly and diffusely, it now moved quickly and directionally. This acceleration mattered because it changed the time scale of ice loss. Instead of responding over millennia, parts of ice sheets began responding over centuries or even decades. Retreats that once would have taken generations unfolded within a few lifetimes. The planet was still slow by human standards, but fast by geological ones. The collapse of ice dams and the draining of glacial lakes contributed directly to this process. Each major flood removed mass from ice sheets indirectly by transferring stored water to the oceans. Each flood lowered ice surfaces and altered flow dynamics upstream. Over time, the ability of ice sheets to rebuild the structures that once stabilized them diminished. Eventually, some ice dams stopped reforming altogether. Drainage routes reopened permanently. Lakes that had filled and drained repeatedly disappeared. The water they once held joined rivers and oceans without obstruction. This marked an important shift. The system no longer oscillated between storage and release. It moved steadily toward release alone. As ice retreated from continental interiors, the land beneath began to rise. The crust, relieved of its icy burden, rebounded upward in a slow but persistent process. This uplift reshaped landscapes once again, altering drainage patterns and affecting relative sea levels. In some regions, rising land partially offset rising seas. In others, the timing of rebound lagged behind, amplifying flooding. These changes added complexity to the transition. Even as global conditions stabilized, local environments continued to shift. Rivers adjusted to new slopes. Lakes drained or formed. Wetlands expanded and contracted. The world remained dynamic. But the source of that dynamism had changed. Ice was no longer driving it. Water, vegetation, and atmosphere had taken the lead. Ocean circulation gradually stabilized as fresh water pulses diminished. With fewer massive disruptions, the conveyor of heat resumed a more consistent pattern. This brought relative stability to regional climates, reducing the frequency and magnitude of abrupt reversals. The younger driest ended, warming resumed and held. Sea levels continued to rise, but the rate slowed as the largest ice sheets dwindled. Coastlines approached positions close to those of today. Continental shelves submerged once more. Estuaries formed, coastal ecosystems matured. The dramatic inland advances of the sea gave way to more familiar tidal rhythms. This stabilization had profound consequences for life. Ecosystems that had been in constant flux gained time to develop complexity. Forests expanded and diversified. Grasslands stabilized. Wetlands became long-term features rather than temporary ones. Animal populations adjusted to more predictable conditions. For humans, this relative stability opened new possibilities. Seasonal patterns became more reliable. Resources could be anticipated rather than constantly chased. Some groups began to settle more permanently, experimenting with managing plants and animals rather than simply following them. These developments were uneven and slow, but they marked a shift in how people related to their environment. The letting go of the Ice Age was therefore not just a climatic transition. It was a turning point in the relationship between Earth systems and life. For tens of thousands of years, survival had meant adapting to cold, scarcity, and unpredictability driven by ice. Now, adaptation meant learning how to live within a warmer, wetter, and more interconnected world. What makes this transition especially striking is how quiet it was compared to the forces involved. There was no global catastrophe marking the end of the Ice Age. No single event announced its departure. Instead, there was a gradual realization, spread across generations, that winters were shorter, summers warmer, ice farther away. The world felt different, but not suddenly so. From a geological perspective, this is how major transitions often occur. Systems resist change until they cannot. Then they reorganize. Once reorganized, they do not easily return to their previous state. The Ice Age let go, not because it was defeated, but because the conditions that sustained it no longer existed. Importantly, this does not mean that ice vanished as a force entirely. Polar ice caps remained. Mountain glaciers persisted. Even today, ice continues to influence climate and sea level. What changed was scale. Ice stopped being the dominant feature of the planet's surface and climate. The memory of the Ice Age, however, did not disappear. It remained etched into landscapes shaped by glaciers and floods. It remained encoded in stories of water and loss. It remained present in the distribution of species and ecosystems. The world that followed was built on foundations laid by ice. Even as that ice retreated, as the transition progressed, feedbacks that once reinforced cold were replaced by feedbacks that reinforced warmth and stability. Vegetation growth reduced albedo further. Soils developed, storing carbon. Wetlands moderated water flow. The planet entered a new mode of operation, one that would persist for thousands of years. This new state was not perfect or static. Climate continued to vary. Droughts, floods, and cooling events still occurred. But the extremes associated with massive ice sheets dominating continents were gone. The Earth had moved into an interglacial phase, one of several it has experienced over its history. But this one would prove particularly significant for the trajectory of life. It is worth noting that this letting go was not inevitable in a simple sense. Had orbital conditions shifted differently, had greenhouse gas levels remained lower, had feedbacks aligned another way, ice might have persisted longer. The Ice Age ended because multiple factors converged, reinforcing one another until the system crossed a threshold. This convergence highlights an important truth about Earth's climate. Large-scale change often requires alignment. One factor alone is rarely enough. It is the interaction of orbital cycles, atmospheric composition, ocean circulation, and surface conditions that determines outcomes. When those interactions align, change accelerates. By the time the Ice Age fully released its hold, the planet had already been transformed by the process of letting go. Landscapes were reshaped, water redistributed, life reorganized. The world that emerged was not simply warmer, it was fundamentally different. Even now, long after the ice has withdrawn to the poles and the great floods have fallen silent, their presence is not fully faded. It lingers, not as noise or drama, but as a quiet undercurrent, something you can sense if you know where to look or if you slow down enough to listen. The floods no longer roar across continents, yet they continue to whisper through landscapes, coastlines, climates, and even the way humans understand time and change. What they left behind is not only physical evidence etched into rock and sediment, but a set of patterns that still shape how the planet behaves today. One of the most obvious places where these whispers persist is the land itself. Valleys that seem far too large for the rivers flowing through them remain scattered across former glaciated regions. Dry channels cut deep into bedrock still stretch across plateaus. Hills streamlined in a single direction still point silently to the path water once took. These features are not actively changing at the pace they once did. but they continue to influence modern processes. Rivers follow routes determined by flood-carved channels. Groundwater moves through sediments, redistributed by ancient surges. Even modern floods, modest by comparison, are guided by pathways established thousands of years ago. Soils, too, carry memory. In some regions, fertile floodplain soils owe their existence to sediments laid down by glacial floods. Elsewhere, thin or absent, soils reflect places where floods strip the land to bare rock, resetting ecological development. These differences affect vegetation, agriculture, and erosion patterns today. What can grow, where water pools, and how quickly land responds to heavy rain are all influenced by events that unfolded long before recorded history. The oceans still bear traces of the floods as well, though their evidence is subtler. Layers of sediment on the seafloor record, pulses of fresh water entering the sea. Chemical signatures preserved in shells and microfossils reveal changes in temperature and salinity linked to meltwater influx. These records allow scientists to reconstruct not just how much water entered the oceans, but how suddenly it arrived. The oceans remember, even if their surface appears calm. Modern ocean circulation also reflects adjustments made during the end of the Ice Age. The pathways by which heat is transported around the globe settled into patterns shaped by post-glacial geography. The positions of continents, the depth of seaways, and the configuration of coastlines all influence currents. Because those coastlines were redrawn by rising seas and flood-altered terrain, the floods indirectly shaped how the oceans move heat today. Climate itself carries these whispers. The sensitivity of the climate system to freshwater input was revealed dramatically during the Ice Age's end. That sensitivity has not disappeared. It remains a fundamental property of how oceans and atmosphere interact. The planet learned, in a sense, how to respond to sudden imbalances, and that lesson is embedded in its dynamics. This is why scientists pay close attention to fresh water entering the oceans. Now the past shows that large rapid inputs can disrupt circulation and trigger widespread effects. The floods of the past were larger than anything observed in modern times, but the mechanisms they activated still exist. The whispers remind us not of inevitability, but of possibility. Beyond physical systems, the floods still whisper through human understanding of time. They challenge the intuition that meaningful change must always be slow. The landscapes they carved demonstrate that rare events can outweigh long periods of gradual action. This has reshaped how scientists think about Earth's history, moving away from an exclusive focus on steady processes toward a broader view that includes sudden transformation. This shift in thinking extends beyond geology. Ecology, climatology, and even archaeology have absorbed the lesson. Ecosystems can reorganize rapidly when thresholds are crossed. Human societies can be reshaped by environmental change that unfolds faster than traditions can adapt. The floods remind us that stability is conditional, not guaranteed. Culturally, the echoes of these events persist in stories, metaphors, and ways of speaking about water. Floods are still symbols of renewal and destruction, endings and beginnings. Even in societies far removed from glacial landscapes, water retains an association with power beyond human control. This symbolism did not arise in a vacuum. It was shaped by real experiences of water, altering the world in ways no one could stop. The idea that land can disappear beneath water, that familiar places can be lost within a lifetime or two, is not abstract. It is grounded in lived history. The floods whisper this lesson across generations, reminding people that landscapes are not permanent fixtures, but participants in ongoing change. There is also a quieter whisper embedded in the timing of these events. The floods did not occur at the beginning of warming, nor at its end. They occurred during transition when systems were out of balance. This timing matters. It suggests that the most dramatic changes often happen not in extremes, but in between, when old structures are weakening and new ones are not yet established. This pattern appears again and again in Earth's history. Periods of relative stability are punctuated by transitions marked by rapid change. The floods exemplify this pattern. They were not anomalies interrupting a smooth process. They were integral to how the transition unfolded. Even the absence of floods today can be understood through their legacy. Modern river systems, ocean basins, and ice configurations do not favor the formation of massive ice dam lakes like Lake Missoula. That does not mean such events are impossible under different conditions, only that the current configuration of the planet reflects lessons learned through past rearrangements. In a broader sense, the floods whisper about scale. They remind us that Earth operates on scales that exceed human experience, but not human relevance. The forces involved were immense, yet their effects were felt locally by individuals and communities. People lived through rising seas, changing rivers, and shifting climates. They adapted, remembered, and passed those memories on. This connection between scale and experience is important. It counters the idea that planetary change is always too slow or too large to matter within a human context. The end of the Ice Age shows that planetary processes can intersect directly with human lives, sometimes abruptly. The whispers also reach into how we think about resilience. Life after the floods did not return to what it was before. It reorganized. Ecosystems changed. Species distribution shifted. Human societies adapted their ways of living. Resilience in this sense was not about resisting change, but about adjusting to it. This lesson is embedded in the landscapes themselves. Flood-carved valleys did not refill with sediment to recreate their former shapes. They became something new, guiding water differently, supporting different ecosystems. The land did not recover its old form. It found a new one. There is something instructive in this permanence. Change, once enacted at sufficient scale, does not reverse simply because conditions stabilize. It leaves a new baseline. The floods whisper that the future is not a restoration of the past, but a continuation shaped by what has already happened. Even silence carries meaning here. The absence of great floods today does not imply that the system has forgotten how to produce them. It implies that the conditions are not aligned. The mechanisms still exist. Ice can still store water. Water can still exploit weakness. The difference lies in configuration, not capability. This understanding fosters a different relationship with the planet, one that is neither alarmist nor complacent. It encourages attentiveness, awareness of thresholds, respect for processes that operate quietly until they do not. The floods also whisper about patience. They were prepared slowly. Water gathered over centuries. Ice weakened over millennia. The dramatic moments were brief, but they were made inevitable by long accumulation. This inversion of timescales is easy to miss. What appears sudden often has deep roots. Listening to these whispers means learning to see beyond immediacy. to recognize that today's conditions are shaped by yesterday's processes, and that tomorrow's changes may already be in preparation, even if they are not yet visible. As the world settled into the relatively stable climate that followed the Ice Age, these lessons did not vanish. They became part of the planet's background knowledge, encoded in its systems and in human culture. The floods no longer needed to speak loudly. Their work was done. Yet they continue to murmur through river bends that seem too wide, through coastlines that hint at lost land, through stories that echo across cultures, and through scientific records that reveal how quickly balance can shift. And perhaps the most enduring whisper is this: change does not always announce itself with urgency. Sometimes it waits, builds, and then moves all at once. The floods of the past remind us that Earth's history is not a straight line, but a series of adjustments. Some gentle, some abrupt, all connected. The ice let go, the water moved, the land remembered, and the world that emerged carries those memories forward, quietly, continuously, shaping everything that came after, including the moment you're in now. Listening in a world that still bears the imprint of water that once waited and then finally ran free.